já todas mais uma vez, muito obrigado ao nosso workshop. Nós temos agora a palestra do professor Chang-Lara, do México. O professor Hector é investigador titular na área de matemática básica do Centro de Investigação de Matemáticas. Doutorou-se pela University of Texas em Austin, sob orientação do professor Luiz Cafarelli. Além disso, foi rico assistente professor na Columbia University. Sua interesse é equações diferenciais espaciais. Em particular, tem interesse em análise e teoria de realidade de equações diferenciais elípticas e parabólicas, equações interdiferenciais, problemas de limites livres, análise de conexões de modelos básicos. O Hector vai falar sobre classical solution to integral equations with zero order kernels. Thank you, Hector.
One second. Okay. Can you see my screen? Hi.
Yeah, it's okay.
Okay, so because I seem I'm having problems understanding what you're saying from perhaps the connection is not so well here at Guanajuato. I'm going to ask that if you have any question, perhaps you can write it or ask to Dison or Clea to type the question. I will receive it in my WhatsApp, okay? Because I think I'm having difficulties hearing what you're trying to say. Well, thank you very much for the introduction. I'm very happy to share some mathematics today at the workshop on analysis and PDE. I thank the organizers, Clea and Dison. I'm afraid that because of my passport, I wasn't able to be there, but I hope to visit Sergipe sometimes in the future. So this work is a collaboration with Alberto Saldaña. He's a good friend from the Institute of Mathematics at the National University in Mexico. We start talking about these fractional or non-local equations where the order is very, very close to zero. No? So usually what we have been doing in integral differential non-local operators is to study this whole family, whole parametrization of the Laplacian that lives between the identity when the order is exactly zero and the classical Laplacian, no? Where the order is equal to 2. So what is quite interesting is that, well, you may study what happens at the both extreme of the regime, no? So one of them was studied by Caffarelli and Silvestre some years ago, and that was the limit when the order was close to 2. And now we're trying to see which results are true when the order is on the other side, when it's close, very, very close to 0. So to start, let me talk about the Laplacian and the fractional Laplacian. No? So there is this very nice formula that allows us to relate the Laplacian with average of u in a ball or in a sphere. No? The most classical result, I would say, is the mean value theorem. No? You remember that a function is either harmonic or superharmonic or subharmonic. This is something that can be evaluated, estimated, comparing the average of u on a sphere or a ball with respect to the value of the center. And actually, you can prove the following identity, which is exact modulus a constant that depends only on the dimension, and can be proved, for example, using the divergence theorem or using the Taylor expansion on the right-hand side. No? So it tells me, it makes this very nice connection between average and the elliptic operators. Now, the fractional version of the Laplacian is something that can be motivated or defined in different ways, no? And I believe that one of the most classical ones is to look at the Fourier symbol. So the Fourier symbol of the Laplacian, if you remember, is C squared. So what happens now if I allow the power not to be exactly 2, but to be any number between 0 and 2? So at 0, we get the identity, and between 0 and 2, we get fractions of the Laplacian. And this is what is called the fractional Laplacian. So this is equivalent, actually, to this integral operation. No? I take u minus u at the center, at the point that where I'm evaluating, and then I multiply by a kernel that is singular of order n, is singular of order n plus 2 times s. No? And this is an operator of order s, okay? And, well, what we want to study now, so as I said before in the introduction, is already well understood, no? What happens when s goes to 1 in this computation, no? You recover the Laplacian, and then when s goes to 0, you recover the identity, no? But in the next term in the expansion, you get s times the logarithm. And this is just a fact that comes from a very simple computation. No, we can be motivated by a simple computation, but it requires some analysis, not to be proved rigorously. It's just a fact that formally, if you take the derivative of delta to the s, well, what you get is the log of delta times delta to the s. And then if you substitute s equal to 0, well, then you get exactly the Laplacian, no? So if we try to define then the logarithmic Laplacian just by the symbol, what we discover is a formula that has 3 terms, and the leading one looks like the previous computation if s was equal to 0. No? So we get this operator that we call is almost, or we could say that has order 0, no? Then you have a multiple of the identity, and then you have a convolution term. So these 2 other terms are lower order terms. If you want to understand, for example, this operator in terms of regularity of solutions of, let's say, a Poisson type equation, then the one that is giving you the crucial information is this one. Okay? And why do we care about this operator? Well, just because if we want to understand the full range, if we want to go close to 0, then this is the one that is becoming more and more relevant. Okay? Up to here, any questions? So what is our goal? What is our theorem that we would like to prove? Well, we would like to look at the Poisson equation, L of u equal to f in some domain omega. We are going to ask omega to be bounded. And then eventually, we are going to add some regularity assumptions on either f and also the boundary of omega. And then we are going to ask u to be equal to 0 on the complement. Okay? So the questions, the classical questions are the solutions of this equation well defined? Do they exist? Are they unique? And then perhaps you can define them in a weak sense. So you wonder how regular they actually are in terms of f and omega. And notice that either for the Laplacian or even the fractional Laplacian, this is more or less something that can be done using a representation formula. There is an explicit way to write, for example, the fundamental solution for the Laplacian or for the fractional Laplacian. But for this one, there is going to be no representation formula. And one of the big issues is that here the kernel doesn't appear in the whole of Rn, it only appears in the ball of radius 1. Okay? And if you notice, one of the reasons that we are forced to choose this ball of radius 1 is that if you have, for example, if you integrate instead in the whole of Rn, no, the integral is going to be divergence generically, no, because you have something that is bounded in the numerator, but the singularity is not integrable at infinity, no? If you have some regularity on U, the singularity is integrable around X, but then you can do nothing about the singularity that appears at infinity. So for that reason, we are forced to choose this domain of integration. Yeah. Okay. So let's. So in this talk, I will discuss, of course, previous work, what has been done recently about this operator, what is interesting. Then I would like to present the well-Posner theory in terms of a family of integral equations. Integral equations are very convenient because we automatically have compactness. So somehow I can restrict myself to family of classical solutions. And then in this family of classical solutions, then I would like to have some uniform control in order to have a limiting problem where we also have classical solutions. Okay. So what has been done about this? One of the first results was this work of Kasman and Mimica around 2015, 14. I think even before that there was a preprint in the archive, and it's very interesting because people have been studying, like in 2012, even in the 2000s, they have been very interested about these integral differential operators, no? But usually what happens is that the kernel, the singularity, is comparable with the fractional Laplacians. And the fractional Laplacian of order strictly bigger than 0 and less than 2, less or equal than 2. Now, the work of Kasman and Mimica allowed to extend the theory to operators of order 0, to operators, kernels, that are not comparable with a multiple, let's say, of the fractional Laplacian. And initially, the arguments that they give to prove regularity of these operators are pure probabilistic. So Kasman and also Mimica were probabilists. Mimica died in around 2016, if I remember, but they were very successful probabilists, no? So, and even here in the abstract, no, you can already foresee that there is some probabilistic arguments happening here, no? And I would say that the PDE counterpart of this argument was done by Luis Silvestre into this, if I remember, was 2012. And it's a very nice paper because in a few words, he said, well, either for fractional Laplacians or even more general kernels, I could say that the equation that we were seeing, let's say L of U equals 0 or L of U equals F, is kind of a mean value theorem. So in a few words, when you do L of U equals 0, remember that this is the integral of U of y minus U of x, and then there is a kernel, no, dy. And if I set this equal to 0, formally, I can split the integral and say that U of x is an average of U around 0. And I said that you can do this only formally because, of course, the kernel is singular at the origin. No? If you split the integral, then it's not going to converge. You're going to have an expression of the form infinity minus infinity. But this is the idea behind this paper, because what he actually uses potential theory arguments. No? The same way that you can prove, for example, a Harnack inequality for the Laplacian using the mean value theorem. In the same way, you get to show here Holder regularity. And this is more or less the argument that we are going to illustrate today for our own problem. Okay? And finally, there have been a very interesting work by the group of Tobias Beth. I think Sven Jaros and Alberto Saldaña were students of Tobias, now they are collaborators. And they have been looking and these whole parametrizations of fractional Laplacian, and they want to get fine properties, no? So find properties of this parametrization implies, for example, to understand the derivatives with respect to S of this fractional Laplacian. Is the next order in the expansion, no? So I would say this was the main motivation also for our work, to look at the Poisson problem for this logarithmic Laplacian, and to say in which, under which hypothesis we can have classical solutions of these equations here with the logarithmic Laplacian and with zero boundary data. Okay? Any questions so far? So let me motivate what could be the existence theorem in terms of a family of integral operators. So what I'm going to do is to approximate my, well, this is, I may call this the logarithmic Laplacian. It's not really the logarithmic Laplacian, but it's the principal part of the logarithmic Laplacian. So allow me to say that this is the operator I want to study. Sometimes I may call it logarithmic Laplacian, no? So this is the equation that we want to analyze. L of u equals f, u equals 0 on the boundary. And what I'm going to do is to approximate, no, the operator by removing a little bit of what happened at the singularity. So what I'm looking at is the original kernel. So my kernel is 1 over distance to the power n, and then I'm going to remove what happens in a neighborhood of radius epsilon, no? So if I call, let's say, L sub epsilon of u equal to this integral minus this ball, then what I obtain is some constant times this integral here, so t epsilon u, no, minus the integral of the kernel, no? So it's the same constant times u, no? And I want to solve this equal to f, no? So if at the end of the day I divide by c, I get a problem of this form, yeah? This f is not the same f as here. This one is the original one. If you want, this one is f tilde is equal to f, I'm sorry. Okay, this is f divided by c. Okay, so my question is, well, can we solve this equation? It seems more manageable because, of course, these are compact operators, no? For every epsilon, the kernel that I'm looking here is just a bounded function. Of course, I cannot have a uniform bound, a uniform control on these kernels, but for each one of them, I have a bounded kernel. So this is a compact operator. And the question is essentially, do you get fixed points for this compact operator? Okay. So we use the Leray-Schauder theory. And we know essentially that, well, let me assume that f is a bounded function. Then I'm going to form the following. I'm going to think my space of functions are going to be bounded functions that vanish outside of omega. So I have this space of functions, yeah? And to make S an operator that goes from the space to itself, of course, I compute whatever f is, S is, and then I delete whatever happens outside of omega, no? And just because of the compactness of T, I get immediately that S is also a compact operator. So Leray-Schauder tells me that if you have a compact operator and you have some sort of maximum principle, then S has a fixed point. It doesn't have to be unique as in the Banach fixed point theorem, but there is at least one fixed point. And what do I mean by a maximum principle? I mean the following. If I have a solution of this equation, T of u minus f equal to some eigenvalue bigger than 1 times u, then u has to be bounded. Okay? And I will show in the next slide how this maximum principle works. Okay? So just to recapitulate, how do you get fixed points? Remember that Brouwer fixed point here and tell you that if you have a compat operator between a convex and bounded domain to itself, then it has a fixed point. So what is our convex bounded domain? Well, I'm going to take the ball of radius capital M, okay, in this space with the L infinity norm. And and S a priori is not an operator from that ball to itself, no? So I'm going to use S, a function that is going to be from Bm to Bm. My original S is not necessarily a function that an operator that has those bounds, but I can just modify it by saying the following. If my image, well, I'm going to rescale also in sign, no? So if S of mu is less or equal than M, then I do the following, and if not, I do this quotient, no? And then it's just a computation to see that now it's well defined. If it has a fixed point, it has to be necessarily a fixed point of the equation that we are interested in, no? S of u, let's say, T of u minus F equals u, okay? So immediately we have that for these compat operators, we always have a solution, okay? So what is still we need to figure out if we can do is this maximum principle, no? So I'm going to give an even more general statement. Instead of saying T of u equals to some eigenvalue and F, I'm just going to look at this case, no? If T of u is bigger than u minus 1 in a ball of radius r, so keep in mind that omega is a bounded domain, and I'm just going to assume omega is contained in Br, okay? And u is equal to 0 in the complement, then the conclusion is going to be that u is going to be less or equal than m for some capital M. And the proof is just a comparison, no? So as is a standard, you take, for example, a barrier. This barrier could be an exponential, and you see that if alpha is sufficiently large, this equation is true. Okay, so this is a computation. Now we're going to take phi equals to some constant minus the exponential, and I'm going to take the constant c sufficiently large such that the barrier is bigger or equal than 0 in the ball of radius 1 plus r. Okay, so now I'm going to compare the function phi and u in the ball of radius. So this is r, and this is 1 plus r, no? Remember that u, there is a... So remember that u outside of the ball of radius 1 is less than 0, so it's automatically less than phi, no? In this margin, let's say, no? And then I'm going to show that phi also has to bound u in the interior of the ball, and therefore there is going to exist this constant m, which is going to be just the supremum of phi, no? So notice that under this construction, no, you get that T of phi is less or equal than phi minus 2, okay? T of a constant, by the way, is always the same constant. Remember that T is an average, no? So in my definition of the operator T is such that T of a constant is the same constant because the constant that I have here makes the kernel with integral equal to 1, okay? So I get this identity, so that means that phi is going to be an upper barrier. So if I have by contradiction that the graph of u crosses the graph of phi at some point x naught, then what we see is the following, that x naught u is bigger than phi. Phi, I know, is bigger or equal than 2 plus T of phi, no? Now, T, remember, is an integral with a positive kernel, so T of phi is bigger or equal than T of u. And we know by assumption, by hypothesis, that T of u is bigger or equal than u minus 1. But this is a contradiction, no? Because here we're saying 0 bigger than 1, okay? And this maximum principle, if you think about, implies this maximum principle that we use in the Leray-Schauder theory. Okay? Questions so far? I'm asking about questions all the time because I cannot see your faces, so I would like to know if everything is fine or if I should go faster or slower, okay? So what we just saw in the previous proof of the maximum principle is just a manifestation of the comparison principle, no? And in general, if you have an operator of this form with a positive kernel, then you have the following comparison principle. That means that if two functions, u and v, have contact at some point, then the operators are ordered, no? L of u at the contact point is bigger or equal to L of v at the contact point. And the reason is clear. If you, well, remember L is a linear operator. If you subtract on both sides, what you're saying is that u minus v has a minimum at x naught, no? Now, if this function has a minimum, then the integral of this minus the place where you take the minimum is bigger or equal than 0, okay? And this is essentially the main tool that we need to use in the rest of the regularity theory, okay? So this is going to be very important because all the time we're going to be using comparison principles with barrier functions, okay? So now that we have an existing theorem for this family of integral operators, now that we know that we can always solve L of epsilon u equals f, our goal is to see that if as epsilon goes to 0, we recover a function, and if that function is regular enough, that is also a solution of the original question, of the original problem. So first, so this implies, or this suggests, I would say, that we should prove some uniform regularity on the solutions of those equations, no? So the first question is, what's the natural regularity that we should have in these problems? So let's take a look. If we compare this regularization, I don't know, this perturbation of the original operator with the original operator, what we get can be bounded in terms of this integral, where omega is the modulus of continuity, no? It's measuring the oscillation of u in the ball of radius rho. Remember that the oscillation is just the supremum minus the infimum, no? So it tells me, so if I say that the oscillation is smaller than whatever omega, then the function has to be trapped on a strip of height equal to omega, okay? So this is just integration in spherical coordinates, no? And I get this quantity, no? So if I want to control this whole family of operators as epsilon goes to 0, I better should have a control on this integral, no? And this is something that is known in analysis as a Dini's modulus of continuity, no? If I have that the modulus of continuity is has the following property, that when you integrate against a function 1 over rho is finite, then we say that u is Dini continuous. Okay, so what are examples of Dini modulus of continuity? For instance, omega rho equal to rho to the alpha certainly satisfy this. This is integral, but this is not like a very fine result, no? But it is even more, well, I would say what is finer, no, is, for example, this type of modulus of continuity. This around the origin, no, the logarithm to the power 1 plus alpha, where alpha is positive, no? If we put here a power less than 1, it's not going to be Dini continuous, but also those modulus of continuity are going to be important in this work. Okay, so this suggests that we should look at these log holder spaces. So log holder spaces are going to be functions defining omega to the reals, such that the modulus of continuity, no, is bounded, so by a constant. This is independent of x, so it's a uniform continuity. And then I'm going to use the log to the power alpha, where this L is this function, no? I just take the absolute value of the logarithmic, but I do a truncation after rho sub 0, okay? So this is a function that essentially looks like this, no? It's concave, and after some point is constant, no? And with that L, I'm going to use powers alpha, no? And in this log holder space, I define the semi-norm as the best constant that I can put here, no? So I take the modulus of continuity and I divide by L to the alpha, and I take the supremum in X and rho, okay? So this is analogous to the holder spaces. The holder spaces are those where the modulus of continuity is smaller or equal than C rho to the power alpha, no? But we have a much worse modulus of continuity, because remember that this function, yeah, well, it goes to 0 slower, no, than any power of rho. No? So if I put here, for example, rho to the power epsilon, eventually this L is going to be on top of the function rho to the power epsilon, okay? So the first thing that we can say and we can notice is that in these log holder spaces, our operators are bounded, okay? So what we notice is the following. If you start with a function which is 1 plus alpha log holder continuous, and is 0 in the complement of omega, and you apply the operator L sub epsilon, well, of course, you get a function that is smooth, but moreover, you get a function that such that is a log alpha norm is bounded by a constant that is independent of epsilon, okay? So this is very nice because it tells me that at least I'm going to have continuity when epsilon goes to 0 in these operators, if I stick to work in these log holder spaces, okay? So the next thing that we should look, and this looks a little bit more complicated, is in which sense are the solutions of the equation L epsilon u equals F, or I'm going to make it simpler here. Let's say L of u equals 0 in V1. Does this imply u to be in L alpha of B1 half for some alpha positive? So this is usually what you get in the first step of the holder regularity for the second order operator, for example, for the Laplacian, if you use the Harnack inequality, no? And something similar happens here, but you need to restrain yourself to these log holder spaces, no? So usually, what is the argument? How do you prove something like this? Well, you want to prove a uniform decay of the oscillation of the solution in dyadic decreasing in geometric decreasing domains, no? So you want to show. So the idea is that if you want to show that u, let's say in the classical case, is in C alpha at the origin, no? Then the oscillation of u decays like C rho to the power alpha, no? And because of the scaling invariance of the equation, this is equivalent to say that if the oscillation of u in the ball of radius 1/2 is smaller or equal than a constant, let me write 1 minus theta, the oscillation of u in the ball of radius 1, okay? So in this case, this strategy is not going to work, and the reason is that the operator that we are looking at is not the scaling invariant. Should have said this before. Sorry about that. But if you notice, what is the scaling of the equation? Let me remind you, L of u, and then I have B1 u minus ux divided by y minus x to the power n dy. And if you do an scaling, that means taking u bar of x equals u of r times x, yeah, then by the change of variable formula, you get that L of u bar is equal to L of u, and there is a reminder term, no? There is a term that comes, an integral that appears now in the ball of radius, r 1 over r minus b1, okay? So every time you do a rescaling, it's not like the Laplacian that you get to rescale the right-hand side, but you always feed something new to the right-hand side, something that is not going to go to zero. It's not a lower order term. It competes with the same scaling with the operator, no? So because of this, you need to be a little bit more careful with the diminishing oscillation. You cannot do a Holder diminishing oscillation, but you can do a log Holder diminishing oscillation. And this is a result of Kasman and Mimica, no? So what I get to show is the following, and it's a very nice paper initially done in the probability setting, no? And it says as follows. So let's say that L of u is bigger or equal than 0. So u is, let's say, a subharmonic function, no? So, and u is bounded from below outside of a ball of radius, or let's say, in the ball of radius 1 plus 2 rho square. Actually, this is a bound that is telling me two things, no? In the ball of radius rho, this is a positive part, no? It's telling me that u is bigger or equal than 0, no? And in the ball of, and in between, no, between the ball of radius rho and the ball of radius 1 plus 2 rho square, the function has a control tail, no? So this is important because when I do the rescaling of the equation, this is going to tell me that the extra terms that appears is not too bad. It's not going to deteriorate the equation too much, no? And the most important hypothesis, I would say, is this one. It tells me that the function u improves, no, is bigger than L to the alpha rho over 2 in some ring, at least half of the measure. But this measure is not the Lebesgue measure, it's just the Lebesgue measure multiplied by, let me say, this is L of x divided by x to the power n dx. Okay, so it's a measure that is quite singular around the origin. Okay, so the conclusion, similar to what happened with the mean value formula when you try to prove Harnack inequality, is that you get to improve u in the ball of radius rho square. Remember that initially our hypothesis says that u is bigger or equal than 0 in the ball of radius rho, and then this is telling me that in the ball of radius rho square, rho is a radius, it's a small radius. So what this is telling me is that I have a positive improvement, no? So this quantity is positive. This is quite technical, and I actually tried to simplify and hide some of the technicalities of this lemma, but I think it's better to understand it in terms of a picture, no? So this is what's going on. So in the ball of radius rho, I know that my function u is bigger or equal than 0, no? Outside of that ball of radius rho, well, it could be negative, but it's not too negative because there is this tail that is controlling from below. My most important hypothesis is that if I look at the ring, let's say, I forgot here, is between rho and 3 rho square, no? So between rho and 3 rho square, yeah? So in some margin, no, around the ball of radius rho, I have that the function u is on top of this level set most of the time, no? At least half of the time, yeah? Then what I get to say is that I get some small improvement in the interior, okay? And the idea of the proof for this lemma is is very, it was inspired by the argument of Luis Silvestre, either in our paper and also in the paper of Kasman and Mimica, and is to look at the barrier argument, no? So the thing is that if we look at this equation, I take let me call this the tail, no? So if I look at the tail, plus I'm going to call this beta because it's like a bump, no? So let me put theta times beta, no? Let's say beta is of order 1, and then I'm going to choose a theta sufficiently small, no? And then I'm going to put the function u, which is going to give me the improvement, and in the region where I have, no? So it's between the ball of radius rho and the ball of radius 3 rho squared, yeah? U. So notice that this function in the ball of radius 2 rho squared is very nice, it's smooth, no? Because in the ball of radius 2 rho squared, the u doesn't appear at all, doesn't play any role, yeah? The only ones that plays a role are t and t, which is 0, and the bound function. And you can compute the operator. And this one is going to give me the improvement, is going to tell me that this function is going to be a sub-harmonic function, okay, for this operator. That means that L of, well, V is going to be bigger or equal than 0 if I take theta sufficiently small, no? So that means that U, remember, is a super solution. I had a mistake here. So U is a super solution, V is a sub-solution, then there is a comparison principle that takes a role, and therefore U has to be on top of this bump, okay? And once you get this improvement, then you do the diminution of oscillation in scalings that, in this case, don't go diadically. I mean, it doesn't go in powers of 2, but it goes in from rho to rho squared to rho to the power 4, and so on. So that's the reason you only get a logarithmic modulus of continuity. So this implies, no, that solutions of your equation are automatically log Holder continuous in any compact set that is contained in your domain omega. And as a consequence, we already have that in our original problem, the one that was approximated by these very nice operators, we get an accumulation point, no? Because all these family of solutions are equicontinuous. Therefore, by Arcela-Scully, the limit exists up to a subsequence, no? So the natural question that we have now is it true that for this limiting solution, L of u is equal to f, and moreover, well, I know that the function u is locally continuous in omega is equal to 0, I should say here locally, and this 0 goes to say that u is equal to 0 in the complement, no? So I know separately that u is continuous in omega, u is continuous in the complement of omega, but it may have still a discontinuity in the boundary of omega. So the next question that we also need to answer is if u has some continuity across, no? So if u is finally continuous in Rn. So perhaps this is better stated the following way: u is continuous in the boundary of omega. And these are actually our contributions in the paper. We get to show that if f have enough regularity, then u is going to be not only log alpha, but it's also going to be log alpha plus 1. And then we get to show that u is also continuous at the boundary. Okay? So this is our contribution, no? And it says that if we assume that the right-hand side, no, is in L1, so this is kind of like saying that it has one derivative in the logarithmic sense, then you get to say that for some alpha that is universal, depends only on dimension, then U is L1 plus alpha uniformly. And the important thing here is that the constant C is independent of epsilon, okay? So this is very nice because now we not only have that U of epsilon converges to U, but also by the continuity theorem that I said at the beginning, L of, well, let me say it this way, no? L of epsilon, U epsilon converge to something else, and because of closeness of the operator, then you get to say that L of U is equal to, we call this F, no? So this is F of epsilon, this converges to something F, then by closeness of the operator, you get to say that L of U is equal to F, no? And that will complete the proof, no? So how do you choose, how do you prove this higher order regularity? Well, you get to look at the equation for L of U equals F, and you sort of want to differentiate this equation, no? You cannot take derivative because you are not assuming that F, the right-hand side, is differentiable, but that is log Holder continuous with the exponent 1, no? So what you look is a difference quotient, no? So you say delta of U is U of X, let's say epsilon E for some unit direction E minus U of X, yeah? And then you would like to get an equation for this difference, no? Actually, delta epsilon U divided by L alpha epsilon, yeah? So this is a quantity that you already know is controlled because of the Holder regularity. But in this case, it gives you a problem, no? Because this quantity that we see here is not going to satisfy the boundary condition, no? So in principle, this is going to be the epsilon U, F divided by L alpha epsilon. And this is controlled because we are assuming that the right-hand side is log Holder continuous with exponent alpha equal to 1. So this is a milder derivative. But the problem is that for these different quotients, the function U doesn't have the zero boundary data, or doesn't have a nice boundary data, no? So what we usually do is we multiply this function by a cutoff function, but that is going to introduce an error term in the right-hand side, no? But this error term can be somehow controlled in terms of if we integrate by parts, essentially, no? So we essentially have to see that we can pass the derivatives to the cutoff factor, okay? So this allows us to show that essentially the incremental quotient of U is going to be at the same time log alpha Holder continuous. Then by interpolation, we get to show that U is actually log 2 alpha continuous, and then we bootstrap, and we can do this all the way up to the exponent bigger than 1. So this is, let's say, the standard Krylov-Safonov-Trudinger argument, no, to get a higher regularity when you have translation invariant operators, no? So I would like to finish here. There is still an important, I would say, open problem. We don't know how to get around that, and it's the fact that this estimate is not optimal at all. We believe that this estimate should be true even if the right-hand side is bounded. So here we are assuming that the right-hand side has this modulus of continuity, but we don't know how to get this estimate, let's say, with 0. Okay, and this is again a feature that the challenge is mainly in the lack of scaling invariance of the operator. And we'll be happy to know more about it. Okay, But thank you very much. Obrigado.
Hello, Hector. Hector, first of all, thank you very much for this very interesting talk. Can you hear me? Here?
I'm sorry, I cannot hear well. I can see you. I see Maxon too.
But can you hear me? No.
Yeah, I can hear you.
First of all, thank you very much for the very interesting talk. And then I have some curiosity at first. The people work with the regional fractional Laplacian, okay? Is the integral instead of the Rn, the integral is over one bounded domain. For example, the P1x, for example.
I'm sorry?
The people work with the regional fractional Laplacian.
Yeah.
And instead of integrate over the Rn, you integrate over a bounded domain, the regional fractional Laplacian. For example, we can choose the bounded domain has the B1, for example. Then we can recover the principal part of the logarithmic fractional Laplacian if you have the regional fractional Laplacian and put the S go to 0.
Yeah, this has been studied as well. This has been studied by Alberto and Tobias. So you, if I understood correctly, you are talking about the regional fractional Laplacian, no?
Yeah.
So this is the one where the integration happens, let's say, in the intersection of the ball of radius 1 center at x with the domain, no? Yeah, this has been studied, but I'm not sure about the regularity, no? I would say, at least in the interior, the regularity is similar, no? Because you get the integral in omega, and then you complement with the rest, and the rest is a compact operator still, no? It has some sort of convolution structure, no? So perhaps it's a perturbation of the original one, or even in this case, when you have the regional fractional Laplacian, it has a more natural connection. I'm sorry, there is a lot of feedback, no? But it has a more natural connection with the eigenfunction, no? Of the Laplacian with zero Dirichlet data, no? And in this case, the eigenfunctions of the classical Laplacian and the regional fractional Laplacian are the same, no?
But my question is, if I have the regional fractional Laplacian and put the S of the regional fractional Laplacian to 0, I recover the principal part of the log fractional Laplacian.
Well, I believe that you will recover not exactly the operator I'm telling you, but you recover the one where the integral is in omega. Notice that it's not the same. Let me Can you see my PowerPoint? No? 1 second. You cannot see my screen, no?
No. You need to present your screen.
Can you see my screen? My PowerPoint? Okay. So what I'm saying is the following, no? So you should get something like the integral of u of y minus u of x, y minus x to the power n dy, and then you integrate in b1x intersection omega. Yeah, this is not the same as b1x of u minus u divided by y minus x to the power n dy, even assuming that u is equal to 0 in the complement, no? Because you also have, no, in the let's say, if I'm stop here, you also have an integral here, which is just going to be this term, no? But that integral is kind of like the identity times a constant, no? So it's still a nice perturbation, is what I'm trying to say.
Okay. The other question is, what kind of solution you work with in this work? Is this called solution?
No, these are classical solutions because I was saying at the beginning that you have a fixed points. No, you use Schauder theory. You have fixed points, and if you notice that the integral equation give you more regularity automatically. No, if you have a solution of PU equals to U minus F, U is automatically at least as regular as F. No.
But if you want to work with the, for example, one Isaac's operator, Isaac's no-log operator, it's possible.
You can that's completely fine, no? Because you can extend the theory to this positive solution because all your arguments are in terms of the comparison principle. And actually, every time we invoke the comparison principle here, we use let's say a solution and a barrier, no? And the barriers are always smooth, no? So you can even apply viscosity solution here without worrying about having to prove the comparison principle for viscosity solutions.
Okay. Thank you, Hector.
Thank you. Hey, Maxon. See you.
Just a small curiosity about this equation. Do you have an explicit example of a solution in the case where I have a constant, for example?
Do we have a specific example? Yes, but I don't remember. No, I mean, we had to compute the barriers, no? when we show the boundary regularity, no? So essentially, for example, let's see, in one dimension, the function script L that I show, which is kind of the 1 over the log, the square root of that is a solution of almost a solution of the Poisson equation. Okay.
I talked to you later about this. Thank you.
Thank you.
More questions? Question mais? Let's thank Professor Hector once more. Thank you, Hector.
Thank you, everybody. Enjoy.
Bye.
Esses esquemas, como estava antes. Isso aí.
Bom, nossa próxima palestra, o professor Cruz, que é professor do Departamento de Matemática da Universidade Federal de Pernambuco, FPE, doutor na UFPE. Sua área de pesquisa é equações diferenciais espaciais, com interesse na rede de equações diferenciais parabólicas não lineares, mecânica dos fluidos e fluidos micropolares. E a falar sobre linguagem de Hegel for Magneto-Micropolar fluidos em MM. Obrigado, Felipe.
Boa tarde, pessoal. Boa tarde a todos. Muito obrigado pelo convite, a Cruz, Giovanni e companhia. Prazer inenarrável estar aqui de novo. Parabenizá-los pelo desafio de organizar um evento híbrido, que eu acho que é o mais difícil que tem. E obrigado também pela oportunidade de falar um pouquinho do meu trabalho, que eu desenvolvi com os colegas, amigos. Eu sou Simão, da Exato, da Recife. Eu vivi com Marco Rojas Meda, da Universidade de Tarapacá, no Chile, e o Paulo Zingana, da Federal do Rio Grande do Sul. Eu vou falar um pouquinho de determinamento temporal para fluidos MHD e micropolar, Magneto e micropolar. Deixa eu ver aqui.
Se chama Magneto-Micropolar. O Magneto-Micropolar nada mais é do que uma variação das clássicas equações.
Seria essa primeira equação aqui, né? Acoplada com a equação micropolar, seria essa segunda equação. Então, nesse sistema, aqui não aparece nada, né? O U é a velocidade linear do fluido, o W é a velocidade de microrotação, velocidade angular de rotação das partículas do fluido. Além disso, a gente acopla também considerar a equação de Maxwell do eletromagnetismo, seria a terceira, diz respeito ao P. P é o campo magnético. Tem também a pressão hidrostática, que é aquele π caligrafado ali na primeira equação. Aquele π mais módulo igual ao quadrado sobre 2, ali alguns chamam na literatura de pressão magnética, de tal forma que todo o restante a gente chama de pressão total, por isso que eu defino ali embaixo Pzinho, π mais o módulo igual ao quadrado sobre 2. P, pressão total do fluido. Um fluido incompressível, ou seja, a densidade constante, consequentemente o divergente de U é zero, segue a equação de continuidade. O divergente de B é zero é uma lei de Gauss, da eletromagnetismo também. Tá? E aí está o problema de Cauchy, as unidades iniciais. I0, W0, B0. Tá? Tem 5 constantes nesse problema, constantes positivas. O μ seria a viscosidade cinemática, Q, viscosidade de vórtice, gama e kappa na segunda equação, viscosidade de rotação, e o nu, coeficiente de resistividade do campo magnético. Ou difusibilidade. São todas constantes relacionadas a propriedades físicas do fluido. F e Ft, ali no finalzinho das equações, seriam forças externas, dados do problema também. Esse é o sistema em 3 dimensões. Deixa eu decidir aqui. falar um pouquinho do caso 2D. No caso 2D, tanto a velocidade linear U quanto o campo magnético B, a gente considera a terceira coordenada de 0. Né? E o eixo de rotação é um eixo paralelo ao eixo vertical, o eixo X3, o XZ. Por isso que no W, as duas primeiras coordenadas seriam 0. Daí você faz uma identificação. No U, você considera o 1, o 2, o campo vetorial em R2, a mesma coisa do B. Já o W seria escalar, no real. Calculando diretamente o rotacional de U e o rotacional de W, nesse formato 2D, obtém-se aqueles casos especiais aqui. Né? Você calcula o rotacional de um ponto com esses dois sendo 0, né? Perdão, essa terceira coordenada sendo 0, dando 0 e 0 aqui, e a gente identifica como sendo uma coisa real. Né? E assim sucessivamente. No caso 2D, o divergente de W acaba sendo 0 também. Né? Porque no caso 2D, você já tem 0 e 0 aqui, e derivaria o W de transformação a X3, mas não tem X3 porque é 2D. Né? Isso é constante. O divergente de W é 0 também. Obrigado, professor. Foi a luzinha? Certo. Aí, bom, estou falando dessas coisinhas, porque. Eu estou falando das equações. Né? Aqui tem um gradiente do divergente de W, que no caso 2D desaparece. Eu mencionei como seria esse rotacional de U e W no caso 2D. E todas essas constantes, onde aparece a derivada de ordem 2, por exemplo, no Laplaciano de Ali aqui, vamos considerar unitárias, para facilitar. Então, gama, kappa, nu igual a 1, mi igual a meio, por exemplo. E joga fora essas forças de Schiera. F igual a 0. Considera-se também o caso do nulo, né? Só para abreviar aqui a exposição. Então, nessa exposição, eu vou falar nesse caso simplificado aqui. Né? Essas constantes assim e forças de Schiera nulo. De tal forma que o caso 2D torna-se esse problema P. Então, o trabalho ele é um caso em Rn, n igual a 2 ou 3. Eu vou falar agora só do caso do 2D. Então, vamos falar um pouquinho de decadimento temporal para esse problema P. Esse problema de valor inicial. Soluções fracas para esse problema. Seguindo. Bom, um pouquinho da história do problema. Lá no ano de 34, esse francês, ele propôs um problema de se demonstrar que a norma da solução das equações de Magneto-Micropolar, a norminha L2, decai para 0 quando o campo é infinito. E, um bocado de tempo depois, o famoso matemático japonês Toshio Kaku, de 1984, provou esse resultado usando técnica de semigrupo. E outros autores também provaram de formas distintas. Uma delas eu chamo a atenção, um ano depois do caso, a matemática argentina Marin-Rubio, que trabalha na Califórnia, nos Estados Unidos, na Universidade de Santa Cruz, e ela resolveu usar uma técnica que ela desenvolveu, chama Fourier-Split. E eu vou tentar explicar um pouquinho desse nome, né, a separação do Fourier. Ela separa a região do espaço todo, a região de integração, o RN, numa bola e no seu complementar. Normalmente seria esse o motivo de não separação. Fourier porque usa transformado em Fourier. E bom, aqui mora o coração do que eu vou explicar. Muito bem, então um breve resumo do método do Schönbeck. Fourier que usa transformado em Fourier. Vou usar essa definição nesse formato, né, sem aquela constante no denominador. Se assim você usa a identidade parcial, aparecerá aquela constante ali, que o π elevado a n sobre 2, é a dimensão. Quando você pode usar a Fourier Split? Para problemas onde você tem uma estimativa de energia, uma identidade de energia, uma desigualdade de energia associada. Então, a derivada da norma em L2 da solução, mais uma constante que vezes a constante do gradiente da solução. Essa norma com índice 2 é sempre a norma L2. Menor ou igual que alguma coisa que depende do tempo. Coisas positivas. Então, sempre que você tem um problema dentro da energia, dá para usar essa risco. Bom, aí agora a separação. Separação porque você separa o RN, né, do espaço, em uma bola fechada, centrada na origem, com um raio que depende do tempo. Raio esse que eu botei ali, raiz quadrada de G sobre G, onde essa função G, uma função maior do que ou igual a 1, satisfaz isso, na verdade. O T igual a 0 é 1, vai ser maior ou igual a 1, derivada positiva, e o principal, né? Porque até então a exponencial satisfazia aquilo ali. Mas o raio vai para 0 quando o tempo vai para infinito. Então, o G sobre G é 0. Então, esse é o truque da chamada. Então, vou anunciar apenas 2 resultados, que eu vou chamar aqui de principais. Tem outros que eu vou comentar no final. Os resultados que eu vou falar agora são para a solução fraca, global do problema. Então, velocidade linear, velocidade microrotacional e o campo magnético, o W. Então, aquela norma. Voltou. Então, essa norma assim, seria a norma da sombra. A norma de U mais a norma de N mais a norma de B. Então, se você pega os dados iniciais em L1 e L2, não é possível mostrar essa taxa de decaimento. Isso aqui, no caso, o problema P, que é o problema 2D. Está vendo 2D. Então, em geral, o decaimento ele é ótimo no sentido que obedece o decaimento do calor. O distante seria menos n sobre 4. Minha dimensão. No caso 3D é menos 3 quartos, no caso 2D, menos 2 quartos, que é menos 2. Então vamos mostrar isso. Se você tem uma solução fraca, dados iniciais em L1 e L2, você tem esse decaimento. E uma coisa a mais, característica da microrotação, deixa eu voltar aqui, é o seguinte. Quando você olha para a equação do W, esse termozinho aqui é W, né, a derivada temporal mais W, tem esse damping aqui, esse amortecimento. Então, dá para você fazer um W, T mais W, dá para você multiplicar pelo exponencial, né, e um fator integrante. Né? Então, seria a derivada no tempo disso. Né? Você multiplica pelo exponencial. O que acontece, então, você tem esse exponencial. Então, isso leva a crer, depois se integra, passa a exponencial dividindo, que o W vai decair mais rápido. E isso é verdade. Isso é verdade, e é o que eu vou chamar aqui de resultado de hoje. E o quão rápido é a mais do que no caso anterior. No caso geral, seria menos 1 dele, mas para o W, e só para ele, menos 1. Ou seja, menos 1 dele, menos 1 dele. Então, 1 meio mais rápido. E os dois coautores que eu mencionei aqui, Paulo Zingano e o Simão, provaram recentemente que isso é o melhor que se pode obter. Se taxa de meio a mais para a velocidade angular, é ótimo. Ok. Com as mesmas hipóteses, não? São quantidades iniciais na linha 2. Muito bem, então, devido ao pouco tempo, eu vou mencionar apenas ideias da demonstração e depois generalizações. Está em curso da prova. Primeiro para a solução UWD, depois do decaimento melhorado. Bom, então, uma prova ilustrativa, heurística, né, palavra chique. Bom, esse parênteses que eu boto ali seria o produto interno em L2. Né, já que são campos solenoidais, tudo em L2 aí. Então, o que é que você faz? Pega a equação do não método linear, a equação do U, multiplica, compromete a equação do U, que é a velocidade. Integra no R2, no R3, a equação que você deve considerar. Então, faz o produto interno. Mesma coisa com W, para a equação de conservação do momento angular, multiplica de W, integra, a mesma coisa para a equação do I. Usa o fato que o fluido é incompressível. Integra por partes, divergente de U é zero, então todas aquelas quantias aí, mais ali, se ela desaparece a pressão, etc. O que mais que eu vou fazer? Vou somar essas três equações. Esse termo aqui, do lado direito, junto com esse, quando você integra por partes e usa o fato que o divergente do P é zero, isso dá zero. Então, acho que é essa informação. Então, pela lei de Gauss, vai dar zero isso daí. E aí soma essas três identidades acima, obtém esse resultado aqui. Aqui eu uso que por exemplo, o integrando por partes, a integral rotacional de W vezes U vai dar a mesma coisa que esse de baixo, por isso que no meio mais ou menos fica um. E assim sucessivamente. Estou caminhando para chegar na identidade de energia, desigualdade de energia, para poder usar a técnica de Schonberg. Se eu tenho um produto interno aqui, desigualdade por X-Schwarz, isso aqui fica menor ou igual para a norma da rotacional de U vezes a norma de W. Como o divergente de U é zero, a norma da rotacional vai dar igual à norma do gradiente de U. E, por fim, a desigualdade de A. E aí, bom, manipula, joga para o lado esquerdo, as coisinhas. Esse meio aqui joga com esse do lado esquerdo, esse daqui é a mesma coisa com esse. Chega na desigualdade aqui, desigualdade do tipo de energia. Então, eu vou conseguir usar Fourier split. E mais ainda, tentando justificar o título, né? Decaimento temporal. Observe que nesses três termos aqui são positivos, você está dizendo que a derivada é negativa. Então, de fato, a solução decresce. E, se você integra no tempo, né, joga fora esse pedaço positivo aqui. Então, essa norma, somatória aqui, é menor ou igual que a soma das normas dos dados iniciais em L2, que é uma das hipóteses. Logo, de fato, todas essas incógnitas do W estão em L2. O Fourier também definido para tudo aquilo. Então, vamos usar o Fourier split. Considerar uma bola, um certo raio R pequeno, desse G vai ser escolhido convenientemente. Usa-se, então, a identidade de conservar. A identidade que aparece aí embaixo. Bom, as normas em L2. A identidade de conservar, ao menos uma constante, você tem a norma do chapéu, do chapéu, etc. É o que se faz aqui. Essa é a desigualdade de antes. Jogando fora pelas normas positivas. E usa a definição transformada de Fourier, essas normas aqui viram essas integrais em todo o espaço. O que mais? Multiplica por G, onde G é a função que aparece aqui no raio, uma função maior do que o igual a 1, ou positivo, preserva essa desigualdade, chega nessa de baixo. Bom, agora que vem a história do Fourier split também, né? Eu vou usar aqui o R2, é essa bola unida com o seu complementar. Agora aqui vai ter mais duas integrais. Essa mesma integral na bola, menos G, integral no complementar. Que é o que eu faço aqui. O que apareceu aí, essa integral toda essa expressão é negativa, né? Porque a integral é tudo positivo, o G é positivo, então eu posso jogar fora essa outra integral ali embaixo. Ficando com isso. Tá? E, bom, eu esteja sendo. Estou querendo ver o que eu explico direitinho, mas vamos lá. O que é que faz? Vou considerar aquela bola. Né? Que se agora está fora da bola. O que está no complementar. Então, o módulo de que se é maior do que o raio. Aí, aqui aparece o módulo de que se ao quadrado. Então, é maior do que o G' sobre G, porque o raio é na raiz. Né? Mas aí você multiplica por menos 1, multiplica por G, vai ficar só um G' aqui do lado direito. Aqui. Por isso que aqui colocou o G'. E subiu que se ao quadrado, porque está se fora da bola. Essa é uma introdução algébrica bem tranquila. E, por fim, o que se faz é observar o seguinte, né? Aqui é uma integral em todo o espaço R2 desse termo. Então, aqui é a integral em R2 menos a integral no complementar sobre a integral na bola. Usando esse fato aqui. Bom, essa é uma desigualdade importante que a gente também tem, que eu vou resumir agora. Esse termo, em cima, é menor do que ou igual a isso. Eu faço questão de dar esse destaque. Essa é uma primeira etapa. E aí eu destaco aquela integral embaixo. Qual a próxima etapa? Estimar estimativas para essas transformadas de Fourier da solução. E aí a gente sabe. Bom, aí tem não vai ter uma conta, trabalhosinha, mas chega nessa proposição, que é aquele integrado, né, menor do que uma constante, uma constante pessoal do que se integral com uma solução. Então, essa constante só depende dos dados iniciais em L1. Pega essa estimativa, substitui na integral que eu destaquei um pouco, que era essa integral. Então, fazendo o pontinho, eleva isso aqui tudo ao quadrado e integra. Chega nessa desigualdade. Esse G' sobre G é do raio. Então, você integra aqui, integra na bola, vai dar a área. Né? Pi vezes o raio ao quadrado. O raio ao quadrado é G' sobre G. Essas fazer as contas. Chega nessa outra integral ali. E agora, acredito que vai ser a escolha do G. Essa conta também é aqui. Vamos fazer a conta aqui. É porque o que tinha antes era esse termo, menor ou igual que G'. G' vezes o que tem aí. Isso vai ficar G' ao quadrado, aqui vai ficar G' ao cubo, aqui ao quadrado, vezes o G'. E aí chega nessa desigualdade. Aqui. E a partir de agora é a escolha do G. Bom, pensando que se você olha para lá dele estou, o caso linear é a equação do calor. O decaimento, a equação do calor é esse. Então agora é meio que uma conta de trás para frente. O que a gente quer obter é o decaimento do tipo menos no meio. Então o caso é igual. E para encontrar o decaimento menos no meio, notou-se que uma certa integral que pode ser legal precisa ser finita. Então, para isso, é necessário obter um decaimento prévio com essa escolha de G. Então, obter um decaimento logarítmico. Então, por que do logaritmo? Porque para obter o que se quer, vai precisar de um logaritmo de trás para frente. Igual aqueles epsilon sobre 2, epsilon sobre 3, já fez a conta, já sabe da escolha. Então, substituir aqui esse logaritmo. Esse logaritmo satisfaz as hipóteses do G, na condição de início. Substituir aqui. Fica com essa expressão grandona. Integra, né, que tem uma desigualdade temporal, integra no tempo, fazendo as continhas, chega nessa desigualdade, né, para transformar de Fourier, usa conservar para voltar para a solução original, né, do W. E passa esse logaritmo ao cubo aqui dividindo, essa outra vez chega nesse menos 2. Esse é um decaimento prévio. Agora vamos em busca do decaimento tipo algébrico, né, menos 1,5. Mas era necessário esse antes. E a escolha legal para o G, para chegar onde se quer, é esse G constante ter mais 1 ao quadrado. Então, faz a mesma coisa que antes, que eu mencionei agora, porém substituindo aqui. G, por ter mais 1 ao quadrado, deriva, substitui, depois integra no tempo, faz algumas simplificações, chega nessa quinta etapa. Chega nessa etapa aqui. Quando chega nessa etapa, nessa integral aqui, o que se tem é esse logaritmo elevado a menos 2. Mas aí a gente faz aparecer esse tal mais 1 aqui e o seu inverso. Vai cancelar. Por quê? Porque essa expressão aqui é a mesma que está do lado esquerdo. Então, a gente quer usar Grover. Esse é o truque do porquê que escolheu o G como sendo aquele logaritmo elevado ao cubo. Porque para usar o PROMAT, esse expoente aqui, essa exponencial tem que ser finita, essa integral tem que ser finita. E é. Então, ela é finita. E aí chega exatamente onde quer. A partir dessa desigualdade acima, escolhendo o G como sendo T mais 1 ao quadrado, usa o PROMAT, chega nessa outra desigualdade. Isto é finito, uma certa constante. Eu passo esse T mais 1 e chega no expoente menos 1. Tirando a raiz, tira no menos 1 meio. Esse é o decaimento desejado para a solução fraca. Mas esse é o primeiro resultado, no caso bidimensional. Agora eu vou mencionar como é que melhora o W, o decaimento da velocidade angular, como isso é esperado, né? Esse exponencial que aparece. E aí você usa a formulação integral da equação micropolar. Seria essa expressão que aí está. Aqui, esse elevado a ΔT é o semigrupo do calor. Então, você escreve isso aqui para algum T0 maior do que ou igual a 0. T0 positivo ou negativo. Bom, eu vou querer obter uma estimativa para a norma em L2. Então, eu vou ter vou usar uma desigualdade triangular, uma desigualdade de hipóteses. Vou ter que estimar rotacional. Você vai pensando na frente, né? O que é que vai usar? Eu tenho que ter uma norma para o rotacional de U, o gradiente de U. Vai precisar de decaimento também, o gradiente. Então, existe uma proporção, a gente prova esse resultado para um tempo grande, né? Para um certo T0. E, bom, como tem semigrupo do calor, vai ser usado também essa desigualdade clássica. Para a solução da equação do calor, com derivadas aqui, do índice de ordem n. E aí, faz a continha. Então, a norma da L2 dessa expressão ali nessa capa 1 e segue para frente. Usa o decaimento que eu mostrei agora na estimativa do semigrupo do calor, na etapa 3. Usa o decaimento do gradiente de U, que é o tempo grande, do decaimento das soluções que já foi amostrado, que é o tempo menos e meio, e chega na integral aqui assim, no final. Agora, mescla, mesclei a evolução de um pouco da ideia da Schoenbeck, agora com a ideia do límite. Separar essa integral aqui no tempo, na metade. De T0 até, primeiro você faz de T0 até T0 mais T sobre 2 e sucessivamente. Põe aí mais um caminho de conta e chega no resultado que eu queria, que é menos 1 meio e menos 1 meio. Menos 1. Essa é um breve resumo desse melhoramento do dado. Bom, e um comentário privado é que aqui a priori é para todo o tempo. É para tempo grande, depois aqui eu digo que é para todo o tempo, mas é porque para tempo pequeno, aí você usa a desigualdade de energia, fica tranquilo. Se vale para tempo grande, vale para tempo pequeno, para a solução. Mas derivada não. Bom, conclusão. Então, em geral, o que se prova no trabalho é que para a solução em Rn, sendo 2 ou 3, dependendo do tipo algébrico do n sobre 4, menos n sobre 4, melhora para o W sempre é menos 1 meio, tanto no caso do D quanto no 3D é menos 1 meio. Né? E várias outras coisas são feitas. Então, mencionei apenas o decaimento das soluções, do WD, mas, aí a gente fez a mais também. A gente considera que dm como sendo derivada de ordem m com relação à variável espacial, e o dela aqui, derivada temporal. Deriva m vezes no espaço, k vezes no tempo. Aí esse m e esse k aparecem dessa forma no expoente. Então, quando m é 0 e quando k é 0, você não está derivando nada, volta ao rescatante, que é o menos n sobre 4. Mas para derivadas, você não consegue para todo tempo. Esse é o tempo grande. E o detalhamento melhorado por W, sempre menos V. Além de U, W e B, são cotas, a pressão também é. Então, a gente também conseguiu o resultado de detalhamento da pressão, de forma geral. Então, N vezes no espaço, K vezes no tempo, onde tem esse detalhamento da pressão também. E, bom, era isso. Já que eu menciono aqui de referências, brevemente. Esse é um trabalho que eu fiz com uma aluna que eu orientei, Michele, é um caso 3D, só para a solução, determinar a solução. Esse segundo é o trabalho que eu fiz com os colegas agora, recente, começou durante a pandemia. E 2 da Schumbeck. Esse terceiro aqui é onde surgiu a técnica dela, mostrou o detalhamento com mais estudos, em 85. E esse da Schumbeck com Wigner, de 96, onde eles fazem o detalhamento envolvendo derivadas do espaço e comprimento. Então, a gente pegou aí esses resultados finais. E eu concluo e agradeço a atenção de todos.
Obrigado, Camilo. Perguntas, comentários?
Olá, tudo bom, Felipe? Obrigada pela palestra, muito bacana. Eu tenho 2 perguntas. A primeira, para você ter existência global de solução, basta dado inicial em L2, mas aí tem um decaimento, você precisou L1. Nos resultados do Lerei do Cátaros também pedem dado inicial só em L2.
A técnica da Schumbeck. Dá para fazer só L2 usando só resultados de detalhamento ideiazinho. Mas o L1 é só para usar o risco.
Eu vi que tem lá um lema que você usa especificamente a estimativa é infinito do
Exatamente. Dá para tornar.
E, assim, pelas contas que você mostrou, você não usa nenhuma inversão, assim, minha pergunta em 3D, é muito mais difícil de fazer? Não, né? Tá.
O mais difícil é o 2D.
Tá.
Porque tem que usar aquele logaritmo. O 3D, né?
Porque geral 3D o problema são as inversões que não estão tão boas. Mas aqui você não usa isso, não. Era isso. Obrigada.
As perguntas, comentários? Então, obrigado, Felipe. Vamos resolver isso com o Felipe. Obrigado. E agora o software isso. O pessoal não pode ver. Passa aqui para a desculpa. Desculpa, não, daqui a pouco vai falar de novo. Vai ganhar mais a sala de volta.
Vou fazer então, técnico, já que voltou o microfone. Poderia fazer o café. Felipe, para essa equação, né, você já tem solução clássica global, porque na visão tem, né? Para essa equação você já tem?
Não recordo. Posso passar a bola? E o Berkeley? Você recorda?
Solução
Ah, sim. 2D, sim. Sim.
Então você assumiu que ela existia.
Sim.
E em R3?
Em R3, não.
Certo. Aí supõe que ela existe se tem um decaimento.
Isso.
Passa o microfone.
Não, a solução para assim. Não, as outras, o resto não são perguntas do a hipótese é a solução abstrata. O teorema considera a solução global fraca do problema fácil. Existe, tudo bonitinho, independente da dimensão. No caso, 2D é global.
Certo.
Responder?
Sim.
Está bem?
Sim, senhor.
Por esse item é de natureza essencialmente parabólica, ou eu posso usar em alguma coisa, em algum modelo hiperbólico?
A natureza, a origem mesmo, é um trabalho na caixão para leite parabólicos.
Certo, mas algo assim, hiperbólico, não. Não desconheço.
A Anne queria comentar, talvez ela saiba.
Não, pô, na verdade eu fiz outra pergunta.
O microfone.
Não, aproveitando a pergunta dele, tem alguma coisa de restrito feito para o paciente estacionário? Preocupação com o paciente estacionário? Tá.
Ele faz um comentário, eu faço, não.
Mas já veio.
Mais um comentário, questão? Então, mais uma salva de palmas, professor Felipe.
Então, pessoal, entrar.
Só fixar em vocês dois aqui. Marcos, se você puder fechar mais um pouquinho, que aí vai sair.
Marcos, mas pega a aula. Pega a aula. É 3,50, não. 3,50. Não, é 3,40. Não, 3,50. Não, não.
É que tá 3,50.
É 3,50, mas aqui é porque tá errado. É errado lá.
Então, mas quem
Cada vez
quiser...
é porque quem for online pode estar sabendo da parte desse vídeo. Melhor esperar o horário, entendeu? Bom, só falta 5 minutos, né? O horário do filme. Cadê? Eu não consigo encontrar. Por aqui não. Fale do jogo amanhã também. Fale do jogo amanhã também. Como vai ser? O jogo.
Olá, pessoal. Só enquanto a gente aguarda o horário, eu coloquei a tabela aqui no estava 3,50. Algumas informações. Hoje a gente vai ter um jantar do evento, às 8 horas, no Sal e Brasa. Todos e todas estão convidados, será muito bom conviver com vocês. E amanhã a gente vai, o evento vai ocorrer pelo período da manhã, porque à tarde vai ter o Grupo Brasil, né? Acho que todo mundo já sabe. E aí aqui vai ser meio expediente. E aí, portanto, à tarde terá uma tarde livre, mas a gente vai almoçar em seguida do evento no restaurante Rei da Sopa da Orla. Então, todos estão convidados também para ir almoçar conosco. E pode assistir o jogo lá também, quem quiser continuar assistindo, quem quiser dar uma passeadinha, amanhã à tarde é livre, tá? E sexta-feira retomamos as atividades normais. Qualquer dúvida pode falar comigo, tá? Aí vamos aguardar agora mais 5 minutinhos, porque a gente tinha que... eu errei na tabela e botei 3,40 para acabar o bloco break, 3,50 para começar a palestra. Foi um erro meu, peço desculpas. E mais 5 minutinhos só. Se precisarem tomar água,
O cara confia lá na frente. Não. Não, mas você paga para mim, você paga pela variedade, pela produção, e pela variedade da sua disposição. Não, você escolhe. Tem que ver com todo mundo. Agora está terrível. Você tudo quer. Pensou, bicho. É só eu que sou.
So, okay, great to resume the section. Okay, so I'm going to resume the section now. And it's a pleasure for me to introduce my very good friend Delia Schiera. She's a postdoc at IST in Lisbon. She did her PhD at the Università degli Studi in Italy under the supervision of Professor Daniele Cassani. She also did a postdoc at Università degli Studi della Campania and Università degli Studi di Roma. She's an expert in PDES. We focus on existence and the history for problems with involves problems. So Delia, please.
Okay. Thank you very much. First of all, I wish to thank the organizers, and especially I would like to thank Pedra, and I would also like to thank Nissan and Giovanna and everybody here, because these days have been really great for me. I really enjoyed spending my time here and visiting your city, your university, and meeting you. So thank you very much. And I'm sorry I will speak in English because I don't feel comfortable enough to speak in Portuguese. Okay, so sorry for that. Today I'm going to present some results I got in collaboration with Isabella Magneto and Giulio Gavise, who are brought in Roma, Università Sapienza. Okay, so the idea is to study a specific class of operators, and which are an extension of the so-called complete Laplacian. So we will try to present a class of operators which extend the complete Laplacian in the sense that they will be also non-local. And we will start with maximum principles and related properties. So I would like to start with the definition of the complete Laplacian in case you are not familiar with it. So the so-called complete Laplacian looks like that. You take the Hessian view, you take the eigenvalues in increasing order, and you sum the k digits, okay? And you can prove that this is equivalent to taking the action and like computing it in the direction ci, doing it for k direction, k generic direction which are orthonormal, sum up, and then taking the maximum. Of course, you can take also the first eigenvalues, or equivalently the minimum, and you get the pk minus. And why this is called truncated Laplacian? Because if you take k equal n, you take all the eigenvalues and you over the Laplacian. So this is why this is a truncated Laplacian. And okay, I would like just to recall a couple of properties of these operators. First of all, they are degenerate elliptic, in the sense that they satisfy this sort of monotonistic condition. And actually, they are strong degenerate in the sense that even if, let's say, the two matrices x and y are different, pk plus and pk of x and y may be excited. And for what it will be important for us is that these operators are nonlinear and non-dimensional. I put here some references that literature is really vast. I don't want to enter too much into details of this because we are going to study an extension of these operators. So just to give you an idea. Okay, so what we would like to do, as I said, we take pk plus. This is the definition we are already seeing. So you see, we are taking the action and computing it in the direction ci, basically. Now we would like to substitute this second order derivative with something which is the 2s order derivative, so something which is non-local. And of course, the model is given by the fraction of Laplacian, which I have put here, just in case you don't remember the definition. And of course, this is non-local. Why? Because the behavior of this operator in x depends on the value of u, not just in x, but in over n. Okay. So the idea is to substitute this red part here with something which is inspired. It is basically the one-dimensional fractional Laplacian in the direction ci. So this is what we are going to do. This is what was done actually stated by the Magneto-Micropolar at top. So they consider this operator I which is exactly the one-dimensional fractional Laplacian in a specific direction psi. So it acts as the 2s fractional derivative. And as I said, we substitute the action which appears in the Laplacian with this new operator here. And we get this ik plus and ik minus, which are the soup and the infimum. And I will just write it here because we need a lot of the definition. Okay, this is just a constant, a suitable constant. Okay, and then minus with the okay. So a couple of properties which were already known or are easy to prove. So first of all, these operators converge to the Laplacian if you take S and you let it go to 1. So this is something you can expect, and actually depends on the specific choice of this constant. One important thing is that even if you take k equal n, you do not record the fractional Laplacian, And actually, you will see that IN plus and IN minus are two different operators. So this is different from what happens with electrophilic actions. And it reveals the rich structure of these kind of operators, which are peculiar. They also satisfy a sort of electricity condition. And the most important thing is that these operators are between the fractional Laplacian and the repeated Laplacian. So they are nonlinear, non-rotational, but also non-local. So you can expect that they will share some similarities with the fractional Laplacian, some similarities with the repeated Laplacians. And I would just mention that we are dealing with the dispositive solutions. Okay, we are entering details. And in this paper by the top, you can find also documentation formulas, we will type results. There is also this very recent paper by Magneto-Micropolar on some recent developments on maximum principle. I would like today to present what we did. The main inspiration is this paper by Magneto-Micropolar, in which they studied the property adaptation. And here we wanted to do something similar for this new class of operators. And I would like to just give an idea here, without entering into details because I don't think it's very useful. Just to give you a flavor of the proofs and what we can expect in this situation, and trying to emphasize the difference between these operators and more standard operators. So I would like to start with something which is specific of these operators. So some continuity properties which we were not actually expecting. We were not expecting something like this, but this is what happens. And what happens is that these operators are not continuous with respect to x. So if you take ik plus minus u of x, this is not continuous with respect to x, even if the function u is very smooth in the domain omega. This is different from other integral differential operators you can find in the literature, and also from the fractional Laplacian and the Laplacians, of course. But we recover continuity if we require a global regularity assumption. So if U is actually continuous in all of R, then actually these operators are continuous, and this is not just a curiosity, but actually, for instance, in this paper by Marin-Rubio, this continuity assumption was used to prove comparison principles. So for our purposes, it was a bit surprising, and we had to work a bit in order to overcome this lack of continuity. And another thing which I think is interesting is that this supremum, which appears here in the definition, is not attained, and it is different from the property Laplacian, where we have a maximum and a minimum. They are attained, here not, and this is somehow predicted. And I would like just to give an idea of the quantum examples, just to give you. Okay, so the first quantum example is in order to show that ik plus u is not continuous. I will just consider the case k less than n, because the case k for n is a bit more delicate, but you can prove it somehow in the same way. So we are considering this function u, which looks more or less like this. Okay, so here the goal is 0, this is the direction Em, and here it is 0, and it is -1 here. Okay, we would like to prove, we take the domain, the goal as the domain omega. We would like to prove that this ik plus u, it is not continuous in 0. And okay, it is almost trivial to see that ik plus u of 0 is 0, because it is immediately negative if you just look at the definition and you consider that u is negative everywhere. So you immediately get that it is negative. And if you take the first k vectors on the standard basis, you live here, and so you see u is 0 here. And so you immediately get that ik plus u is 0. But if you take some points here, which let's say converge to 0, you can prove that that is inequality holds, so this limit is strictly negative. Why is it so? Just really a sketch. So again, we are here, so we have these points 1 over n Pn, which is here. And then you take a direction psi. Okay. And you want to compute this guy here on this line psi. And what you see is that, let's say, the points in this outline, you can write them like 1 over n Pn plus tau c with tau positive, and here you have point 1 over n minus tau psi. And you see there are two values, tau 1 and tau 2 of them, such that if you are below, if tau is strictly below tau 1 of n, let's say you got the points here and with the minus tau with the side of it. Then you have a second value tau 2, such that here you are outside the wall, but here you are still inside the wall. And then, okay, you are inside. So you split this interval here into these three intervals, and you actually make explicit computation in order to estimate. And you see that this value can be estimated by this interval here, and this tau 1 value can be explicitly computed, but what is important is that it can be estimated by this quantity. And now you just do the integral and you let n goes to infinity, and you see you get this negative value. So this limit is still negative, but we already seen that ik plus u in 0 is 0. So this shows that this operator is not continuous in 0. The second counterexample is somehow similar, and in order to show that this operator, let's say this supremum is not attained, just in the case k equal 1. So it's more or less the same function, but in place of -1 here, we take e to the power minus x again, also here. And now the idea is the following. We have, let's say, this direction psi. And what we would like to do is that at 0, the supremum is not attained. Okay. So you explicitly compute here along this line, and you see if this scalar product is 0, so if you are living here, then the function is 0, so this interval is 0. But if you are in any other direction here, you have an explicit expression, which is given by this f, which is written on the next slide. Okay, and you can explicitly compute the supremum, and you get this quantity. So basically, what happens is that this I psi increases as this inclination decreases. Okay, but here the function is 0. So this is why you have discontinuity, and you can obtain the supremum. Okay. So, yeah. So this is just a property which we are not expecting, that it is really related to this kind of operators. And now I would like to see a couple of words on maximum principles, which were our main purpose in this project. So I'd like just to see a couple of words on comparison, but actually we'd like to focus on the strong maximum minimum principle, which we will see is not always satisfied. And in some sense, this is resembling what happens for quantity Laplacian. And also, I would like to show us stronger properties which is satisfied by some of these operators, but not all of them. Okay, as I say, just a couple of words on comparison. You can find some proof in this direction, but in this paper by the Rossi, under some additional assumption, but we managed to give a different proof. The comparison principle actually is not a big problem, and by using the comparison principle, you can get a weak minimum or maximum principle, in the sense that if a plus minus u is below is negative and u is positive outside the domain, then u is positive also inside, so a sort of sign propagation property. What is interesting is the strong minimum principle. What I mean by strong minimum principle in this context, if you know that the operator is negative, that u is positive everywhere, can we say that it is strictly positive or constantly zero in omega? And this is not always the case, it depends on the k, and if we are taking the plus or minus operator, so you see we have a rich structure. And this is what happens. So if you consider the operators ik minus with k strictly less than n, then you do not have a strong minimum principle. Why this is so? This is a really easy proof. You just take phi, a one-dimensional function which attains the minimum of some point in R, and you like replicate it in all of Rn, taking 2x equal to 5x n. So you see that this function that it is constant in any other direction apart from xn. So if you just consider the first k vectors of the canonical basis, you just have this equality, and this quantity here from the definition is positive equal 0. So you immediately get that this ik minus u is negative. And here it is crucial that we are dealing with k strictly less than n, because of course if you take also the direction n, then you actually see the behavior of phi. So here it is almost trivial to find a quantum example for the strong minimum principle. But if you take k equal n, or if you take ik plus for any k, then you have a strong minimum principle. Why? Okay, I would like just to give a sketch of the proof. So you assume to have all the hypotheses of the minimum principle, and you assume that this conclusion is not satisfied, so you have a point which is in which it is 0, and some point in which it is positive inside omega. And okay, you can choose, trust me, you can choose a ball inside the domain such that u is positive inside it is a small ball, and you have a point x1 such that here u is 0. And what's the idea here? Apart from the technicalities, is that since we are taking, you are living in a space of dimension n, and you are taking orthonormal basis of dimension n. So, independently on which basis you actually consider, you have at least one direction which goes inside the ball. So just think about a sphere in dimension 3. And if you are considering orthonormal basis of dimension 2, of course you can take the plane which is tangential to the sphere. If you're taking 3 orthonormal vectors, then at least one of them must enter into the sphere. Okay, so that's the idea. Taking, knowing this fact, taking this specific direction, and estimating it from below by a positive constant. Actually, you can say, of course, it is important that u is positive here inside this book, but you can actually bound from below by a positive constant, which do not depend on the specific choice of the orthogonal base. So this is why for k equal n, you recover the minimum principle, the strong minimum principle. And okay, you can do this. Yes, you can do something, let's say, a bit more complicated to prove also for ik plus, but actually this, let's say, this property for ik plus will follow also from what I will say in the next slide. So I will just keep this, and I would like to say a couple of words on this stronger property, in the sense that the minimum principle told us that if the operator is negative and U is positive, then you can prove that U is strictly positive in omega or constant 0 in omega. But actually, if you take IT plus, then you can say that U is equal to 0 everywhere if it is not strictly positive in omega. So it is a stronger property which is satisfied, for instance, by fractional function. This is satisfied by IT plus, but this is not satisfied by IN minus. So you see that we have a really rich structure in the sense that IK minus with k strictly less than n does not satisfy the strong minimum principle. IN minus satisfies the strong minimum principle, but not this stronger property. And IK plus satisfies also this stronger property for n in k. Okay, why this is so? Okay, for IK plus, you just take the definition. You know, okay, you know that this is negative. You take the definition. You choose any of the normal basis. You now use that U is positive, so you immediately get from this easy inequality that U has to be 0 in any direction, right? It's the only possibility. And so you are basically done in 3 lines. While for IN minus, this is not the case. You can take an explicit counter example, and this time it looks like this. So it is 0 inside this cross, and it is 1 here. You take the ball to be the domain, and you see that if you take as a specific choice, IN minus is the infimum over all possible choice of the working on the basis, and if you take the canonical basis, you are living inside this process, so actually this is 0 immediately. And so this is why for IN minus we don't have this stronger property. Okay. Now, I think that I have 5 minutes. Maybe a little more. So I would like to say a couple of words on other 2 results we got without entering into the details. So I would like to say a couple of words on eigenvalues and their relation with maximum principles. So just to start with, I would like to recall the definition of principal eigenvalues for a linear operator. So for just a second, forget about these weird operators. Take a linear operator like this, and one define the principal eigenvalue in this way, taking the infimum of this integral here. And okay, this number has a lot of interesting property, but for our purposes, it is important to notice that minus L plus lambda satisfies the maximum principle if and only if lambda is strictly below this lambda 1. Okay, what can we say for nonlinear, non-variational operators? Of course, we cannot give a definition like this. So what one can do? One can take the definition by Benzini and Varada and adapt it to the case of nonlinear operator. This was done by Schiera. And what is interesting is that in this case, you don't have just one principal eigenvalue, but you have 2 principal eigenvalues. One is related to the maximum principle and one to the minimum principle. And of course, the maximum and minimum principle are not the same thing in the setting of nonlinear operators. And you have 2 values which cannot coincide. In general, do not coincide. And so what we are expecting is that also from this class of operator, which are nonlinear and variation, we should have something similar. And so the idea was to give a definition of principal eigenvalue, which is based upon this deterministic Varada. And the definition Aí eu vou dar aqui.
Aqui a da luz está funcionando. A visitante da luz está funcionando. Aqui já. Voltou agora, foi? Agora tá. Agora tá. Tá marcando também. E provavelmente não faria. Mas a nossa questão de tela era porque tinha bastante de fora. Caiu mesmo? Tá lenta, né? A minha prima está lenta. Tá feito aí? Reiniciar. Voltou? É, que eu vou projetar lá mesmo. Voltou? Voltou? Veja se está o slide dela. A apresentação dela.
Não, saiu.
É o Pedro, a pessoa. Olha, tá esperando. O Pedro já está esperando. Vamos local.
they are finite. This is the important thing. And what we proved is that ik plus mu satisfies the maximum principle if mu is below mu k plus, and the minimum principle if mu is below mu k minus. So these values are actually the correct, the right notion of the principal eigenvalues for these operators. And okay, maybe I don't know, I will just skip this part of the proof. It's just actually a matter of choosing suitable test functions, suitable barrier functions. But I don't want to enter too much in the details. Just to mention that these results, apart from the proofs, but the results are more or less similar to what happens with the Laplacian. So we have somehow a similar behavior, which is somehow expected because the nonlinearity of the problem comes into play importantly. And so, okay, in the very last part of my talk, I would like to say a couple of words on another important property of these eigenvalues. So, okay, you can expect that if you call them eigenvalues, there must be an eigenfunction associated to them. And this is not trivial to prove actually, and we managed to prove something only in the case k equal 1, and when the domain satisfies this property, which I just recalled, so we called it the uniformly convex domain. It is like the intersection of those. And okay, so what we do is this theorem over here. You take a domain which is uniformly convex, S is above 1,000, and then you can find a positive function which is an eigenfunction for mu1 plus, and you can also find correspondingly a negative function for mu1 minus. And to prove this result, it is actually crucial to prove some irregularity estimates for the solution of the associated derivative problem. And what one proves is that a solution of this derivative problem is order continuous of order 2s minus 1. And this is actually more resembling the fractional Laplacian, for which you have a similar regularity, whereas for the quantity Laplacian, you have each its regularity so much more than this. But here, the non-locality comes really into play, and you get a regularity which is the same as the fractional Laplacian. And so I would like just to give a sketch of the proof. And okay, so the idea is to construct a suitable test function, a suitable barrier function. Okay, this is like the explicit analytic expression, but just okay. So just to give you an idea, the function v looks more or less like this. So it is constant outside this ball radius r0. Okay, and here looks like this, where the shape inside is given by this w, which is chosen exactly in order to have this 2s minus 1 over here, because I recall that we want to prove all the estimates of exactly this exponent. And so what's the idea? You define v y0 of x for any y0 close enough to x0. You define this y0 in x, given by this expression here. And if you prove this Reed inequality, then you're basically done. Why? Because it's just a matter of computation. Y0 of x0 is u of y0 plus sv x0 minus y0. And now you can choose x0 and y0 close enough in order to be, let's say, inside this ball here. So you just see the behavior of w. And so you basically substitute here w. And you have u y0 plus l, actually a minus 0 minus y0 to s minus 1. plus L 0 theta. And now you see that if you take this on the other side, you get exactly this part here. You can just forget about it because it is positive, and so you immediately recover the regularity. So everything reduces to proving that this random inequality holds true. And how you can prove it maybe is to use a comparison principle. We already know that U satisfy the problem. We know what U satisfy. We would like to show that y0 is a super solution for the same problem. And so, if, okay. Okay, so we would like to apply the comparison principle. So you have y0, you have a ball of radius rho, and you have here the meter. And we would like to apply the comparison principle on this set here without the point y0. And so what you want to show? You want to show that B actually y0 is a super solution. So you want to put this first item here, and it is a matter of explicit computations. And this is why we are doing just with the case k equal 1, because here it's already a mess, and as you can expect, when you increase k, things get a bit weird. And you also have to prove these inequalities outside the domain you are considering. So if you are actually outside this ball, the things are more easy because you can just exploit the monotonicity of B. But if you are in this part here, then here you really need to use the uniform complexity of the problem. So you really need to know that the domain is of this form. And why it is so, okay, it is a bit technical, but see here, it is where really you see the boundary. If you're living here, you don't really see the boundary of omega. Here, you would like to prove regularity up to the boundary. So in order to really deal with this boundary, you need to assume some condition of the boundary. More or less, this is the motivation, let's say. But an observation is that if you don't need regularity up to the boundary, then you can prove regularity also for more general domains. You don't need this condition here. So we use this uniformity complexity just for proving regularity up to the boundary. Okay, and now really to conclude, I would like to just give you an idea of some working progress, some possible extension of this class of operators. Okay, here we are considering no local diffusion in one-dimensional spaces, but one can also try to think about operators which are we have that have local diffusion in a space of dimension k. Okay, more than in this case, and see what happens. And also more general operators like mixed operators in which you consider just one direction and then a plane. And so we think that these kind of operators are interesting, at least from a mathematical point of view. And we are trying to study a little bit more and try to understand at least if this maximum principle still holds and in which sense they hold. And so it's all where.
Any questions? Any questions or comments? You can ask in Portuguese, English, Italian, Chinese.
Délia, muito obrigado pela palestra, muito interessante o tema. Délia, na verdade, duas perguntas estão ligadas são coisas que estão ligadas no começo do tema. No último operador que você apresentou ali, na verdade, uma pergunta que eu desde o começo da palestra. você apresentou ali, se o K for igual a N, aí ele vai coincidir com o fracionário. O último que você apresentou, né? O que você trabalha, não, né? Você conhece outro que seja um tipo truncado, que quando o K seja igual a N, vai dar o fracionário? Na literatura, não, mas é uma curiosidade.
Não conheço nada disso. Não sei.
Certo.
Acho que não tem nada.
Outra coisa, você conhece algum resultado para o truncado laplaciano mesmo ou para o seu, né? Ou seja, que mostra a existência de soluções fundamentais? Like Laplacian, one solution that blow up in the origin, go to zero in the infinity, and there is a homogeneous to some degree. Like the modulo of x to minus 9. And
But I think that should be something similar to the Laplacian, but I'm not really sure.
okay. Thank you, Dan.
Any other questions, comments? If not, let's thank Daniel again.
Hello? Can you hear me? Hello, can you hear me?
Professor?
Hello?
Yeah. Can you hear me?
Yeah, I can hear you. And you? Can you hear me?
Yes, perfect.
Cross fingers.
Just a minute.
Influenciando a funcionária. Mas assim, não é um resultado que interessa muito, né? Ele produz influenciando a funcionária. Ele produz influenciando a funcionária. E aí você poderia definir um truncado, como se definisse o truncado do Laplaciano com esses termos não locais. E aí, quando, por exemplo, se você pegar aí ele vai define esse e pega a função f das matrizes na reta, como se fosse um fluido olímpico. Quando a f é o traço, vai ser exatamente o fracionário da Laplaciano. Entendeu? Porque ele pega E e E, aí são os eixos coordenados do Rn. Entendeu? Aí Aí ele vai dar as coordenadas da matriz. Entendeu? Aí, de repente, esse aí coincidiria com o fracionário, quando o K fosse igual a N. Na verdade, era essa a minha pergunta. Era se alguém já traduzir esse tema com esse. Então, aí, na verdade, ele trata de regularidade. Você quiser, eu mando para você. Full professor square, full square professor.
I pass. I'm trying to move along the presentation. Can you see my change?
Yeah, we can see the first page.
Only the first page, but if I move, I'm moving, but you cannot?
No, we can't see it.
Why? Why? I'm trying to move. Oh no, it's not moving. I can see. Let me try again to remove and to start to share the screen. Sorry, just 1 minute.
This movie is online.
Não, já está tentando mexer em coisa.
No, cannot see. I mean, we can see the first page. Yeah, now, yes. But, who is? Okay. Only the first line.
I'm.
Não, quem movimenta é aqui, quem movimenta aqui. Não, quem está movimentando é aqui.
Mas ele não consegue.
I'm trying to move, but.
Okay, just a minute. The technical difficulties. Professor, in the platform there is this option present. So can you look at it?
Yeah, I
and put your file there.
In present, I have to share a screen, doesn't it?
Yes, is it the same? Yeah.
I try to.
Okay, now you can see. Okay,
Now it seems to work.
Can you try to move the? Can you move the? Let's see. Can you put the full screen? Yeah, can you try to?
So can you see it now? Because if I change to.
Yes, okay, yeah.
Okay.
Okay.
Then,
Okay, let me just present Professor Pedro Marin-Rubio. He's a professor at Cruz de Sevilla. He did your PhD at Universidade of Sevilla under the supervision of Professor Tomás Carvalho and José Real. His area of interest is PDES, in particular the existence, initially, and stability of PDES, asymptotic behaviors of dynamic systems, Navier-Stokes equations, and some uncontent topics. So, Professor, feel free to start.
okay. So definitely, can you hear me, no?
Yeah.
Okay, because technology is, bom, boa tarde. Eu quase pouca coisa que eu posso falar em português. Se eu estou muito longo, eu começo a falar portunhol e após de um minuto eu falo totalmente em espanhol. Então, vou trocar para inglês, de acordo? First of all, I would like to thank the scientific committee and the organizers of the meeting for the opportunity to deliver this talk here in the meeting. We have checked with the previous speaker, with Professor Delia, that technology has some counterparts, isn't it? During 2.5 years with the pandemic, we have been completely closed in a terrible situation, and internet at least allow us to have some meetings in the distance when we were completely closed, or for some people that by different reasons we cannot move immediately by some duties. So I thank that the organizing committee allowed me to deliver this talk via online. Hope you can receive it, and I will try not to make it longer, just in case of the technology and so on. The topic of the talk is concerned with some sort of different papers that we have tried to develop during the last few years. It was work done in collaboration with Tomás Carvalho, who is the main researcher in our group, and with a former PhD student we had, that is Marta Herrera Cobos. For this presentation, the first slide that I wanted to put, and I hope now you can see when I move the slides, is something that was funny for me when I found that in a book by one famous colleague we have, Jürgen Jost, that in one of his books on mathematical method for biology and neurobiology, he starts immediately in the first page with this. He put just one set of different theses and says what happened when we deal with modelization in a biological situation. We have a discrete structure, we have a continuous structure, we may have a mixture of randomness or deterministic. Even we have the thesis number 5 is very nice for me. There are only some concepts, some information, but they are relative. They are not absolute ones. Are you sure you can hear me?
Yes.
Sorry, I received some echo. The point, because I put this, I'm not an expert in modelization in biology, of course, but it's because when we are concerning with some PDE model, usually we are very focused on the application. If we are dealing with some problem in fluid mechanics, for instance, in the physics, we are not going to violate any thermodynamic law. However, here we have a different situation. We are not going to violate the laws that appear in nature, but we are more relaxed and we can feel a little bit free to introduce some modifications in the problem. Okay? This is the difference when we are playing with PDE models in some biological situation. That was my first problem. This is also borrowed slide. This not come from me. This come from Professor Benoit Pertin, and it contains one of the most famous in the last decades problem in PDEs applied to the biology, to the nature. What happened with chemotaxis? What happened when we try to study models concerning with tumor or with growth or with any kind of chemoattraction or chemorepulsion? What happens if we have some population of cells and if we have some food, some oxygen or any kind of chemoattract? This is a traditional model with many more variations and hundreds or thousands of papers in the last years. This is the famous Keller-Segel model, where you see that the first equation appearing there written in blue in the bottom. It has a mixture of the parabolic structure where the diffusion want to make that the cell population diffuse, and the last term that implies a transport equation that indicates that the cells move, of course, in the direction of the food. The cells and the n variable moves in the direction of the concentration of the food, the main concentration that is given by the gradient. When you consider the system and you substitute some Poisson formula and you obtain what is C in terms of some integral in about n, you can substitute the second in the first equation and you obtain immediately a PDE model with a non-local effect. There are many models with non-local effect, and of course this is too complicated, at least for me. It's too complicated. There's a lot of very good mathematicians doing a lot of models with this. In the previous talk, we have seen Professor Delia talking about the fractional Laplacian, similar operators, etc. So what I present is some free interpretation of non-local PDE problem in a PDE toy model, if you want to think about it. And it is based on some results of some colleagues that I'm going to present right now. So my goal is to present briefly, not with the full detail in all these slides because of the time. What have we tried to focus in the last years of problem with a non-local effect in a much more very simple way? What kind of results on existence for this PDE problem we obtained? What happens if we try to obtain more regular solution? Because it is useful for numeric people and for different purposes. And because we are dynamical system people, in the end, we were interested in the long-time behavior of the problem. So I will present some results concerning the attractor for the problem. This will be done in two settings. One in L2, in L2 space, and later with some regularity in H1. But the change from one space to the other contains some special difficulties, at least for us. And actually, if I have time, I will try to tell you what are the last problems that we are trying to analyze right now. Okay, the kind of different models with non-local effects, with fractional Laplacian, with convolution, Professor Julio Rossi, who is part of these committees in this meeting, from many people, is appear along the literature in the last few decades very often. In biology, what I try to think about, having in mind the Keller-Segal model, is that we have population of any kind of biological species, things about bacteria, for instance, that it is moving around, having some sensor, and trying to move according to the movement is developing according to the receptors they have, all what's happening around. But for me, the Keller-Segal model is too complicated. So what we tried to study was a model that just contained the non-local effect in the diffusion appearing in a classical parabolic problem. Later we can discuss about dissipative wave hyperbolic equations and so on. Or it can be also related to numerical assimilation of viscosity in fluid mechanics or some many other kind of concepts. But my motivation comes from biology and from the point of view of thinking what happened with a population that see that a lot of the people of that population is moving around some special part of the dominion. So the classical model that justify and is the keystone to start with of our problem is this one. This problem appeared in a series of papers by Chipot and collaborators. It is a classical parabolic equation, let's say even a heat equation, but in front of the minus Laplacian, it contains some extra term that is a function composed with L of U. L is an element in the dual of L2, and U is the whole population, the concentration of the population. So L of U is looking what happened to the whole population. So in terms of if the population grows in some part or in other, it makes that the viscosity that is affecting the diffusion move in different steps. Sometimes in a crowded sense, and some other type in a low density sense. These are some papers by Chipot and collaborators where, well, they deal with this kind of model, and we try to develop the same kind of analysis for a model where the problem was a little bit more complicated, starting from that. In this previous work by Chipot and collaborators, they studied the well-possedness of the problem, existing and uniqueness of global solution, stationary solutions, or their intervals where the evolution solutions of the problem are moving around and in what direction. It was a complicated, but not so much complicated problem because F was independent on the unknown. In some cases, some very particular cases, they have a Lyapunov structure, but it is not so often because the term L of U used to, it depends on time, of course, and it is not possible all the time to obtain a Lyapunov function to deal with grading structure and so on. Only in some beam equation, if I remember well, in damped wave beam equation and structure of dissipative hyperbolic stuff, then you can try to use Lyapunov structure, but very little, not in this setting. Some other results, the previous ones, the first one, to my knowledge, containing results about attractors, that it is one of our business, were obtained by Andamio Bono and Ruggiero for this problem appearing here. For us, the kind of perturbation that we want to study was more properly not a heat equation, but a reaction diffusion problem, where the F appearing in the right-hand side depend on U. So for that, we started all the study again and tried to obtain well-possedness in the sense of Hadamard, existing uniqueness when possible, and continuity with respect to the initial data for weak solutions in a global sense, global in time. If possible, we try to obtain regularization property as in any parabolic equation. We are able to do that. And by some reason that I will explain during the talk, we first study the case with F being sublinear. Because there are some technical problems that appear in one posterior slide. I will show you later. The method to try to study the system of tractor is based on the obtention of energy equality. We were able to obtain that. We were able to obtain fixed points. That was stationary solution, and the exponential decay of evolutionary solution to the unique stationary solution under additional assumptions, where A and F now need to be Lipschitz, a particular case, even more a particular case. After that, when the conditions are not so strong on A and F, we were able to establish the existence of minimal pullback attractor in L2 and in H1. But for that, of course, paying the price of having more regularity for the right-hand side, the term H. Okay, just have a flavor of some of the results, and I will try to skip some of the slides. This is the standard way where the uniqueness and continuity with respect to the initial data can follow. If we assume that A is locally Lipschitz and F satisfied, for instance, to be C1 and controlled by the left from below by some constant, the derivative, or if we have this condition written in blue, then we are able to obtain uniqueness in the following sense. Even if we have a local term in front of the Laplacian, since the solution is going to be continuous, because U prime is going to be in L2 in H-1, we are dealing with a Dirichlet boundary condition. We have energy equality. With the energy equality, if we try to study what happened with the difference of two solutions, I'm skipping the system of solution because it is very, very similar to other more general case. So I will discuss it in the more complex case that will appear later. The difference of two solutions, even in this setting, with the energy equality, allows us to obtain this inequality where we can apply Grunwald lemma. We have just made use of the subtraction of the two equations and using that L of U, L is a linear operator on L2, and the good estimates we had for the weak solutions were L infinity in time, L2 in space. So in the end, after some standard Cauchy inequalities and so on, we are able to obtain the standard inequality that you can see at the bottom. And then from Grunwald follows both the uniqueness and the continuity with respect to the initial data. The similar in this same setting with F sublinear, but still also with Lipschitz condition and A also Lipschitz, we are able to obtain stationary solutions for the problem. A stationary solution is an element satisfying that. And actually, every stationary solution must satisfy this bound, where the double bar norm means, as usual, the norm of the gradient, the norm in H1, 0, right? The sketch of the proof follows by considering in a finite dimensional setting in the Vn space an operator that we can prove that it is continuous and that satisfies the good sign condition that appears at the bottom of the slides. Then it means that in a ball with a radius epsilon, it happens that Rn of U times U is positive. Then we can use a corollary of Brouwer-Fisher point and we obtain a solution in the Vn space. And so, since we have a good estimate obtained in a similar way by epsilon, we can extract a subsequence and pass to the limit. When we stress a bit more the condition on the little m, that it is a constant, that it is bonding from below the non-local viscosity function A, if it is bigger than some constant related with the Lipschitz constant of F, the first eigenvalue of the minor Laplacian, and it is also controlling some other terms concerning the L function, the Lipschitz constant A, and the epsilon constant appearing as a priori bound of every stationary solution, we obtain in the same similar way uniqueness. Even more, we are able to obtain that when this stationary solution is unique, the evolutionary solution, the weak solution of the problem, converges exponentially fast to the stationary solution. And the proof, again, is just considering the first energy inequality and adding and resting some element combining the non-local term and the Laplacian of the U star, the weak solution that we have obtained. So in the end, everything indicates that the presence of this simple non-local term in front of the viscosity is not so bad. It seems in principle in this way, but still at this stage, I have left the assumption of F being sublinear or even Lipschitz, right? There's one reason to do that. We separate, we split the problem in the sublinear case of F and the non-sublinear case of F, that is appearing now in this slide, because we have technical problems when we want to obtain more regularity. I have skipped the proof or any comment about the system of weak solution and the regularity property, the system, therefore, of a strong solution, and the system of attractor, because all of that is very, very similar to this case, just with one difference, one technical difference about because of some technicality concerning the non-local term. Let me show that in a few minutes. The case of F being not just sublinear before is going to be a reaction diffusion like nonlinearity. Now we are going to remove not only that F is going to be not sublinear, more general, but also we are going to remove that A to be locally Lipschitz. That was appearing as one of the previous conditions. We are not going to assume that anymore. We would like to think in the idea that a big change in the viscosity behavior of the problem allow a population to grow immediately. For people who are working with tumor growth, they use sometimes Gompertz models and very, very quickly growing functions to try to model the situation when the tumor grows in a very big way. So we wanted that the A is not controlled. This implies that we are going to lose the proof of uniqueness that we have seen previously. And we are going to deal with the multivalue framework because we don't have a unique solution anymore. Now we combine the nonlinearity F that we are going to use with a family of problems where the terms are not completely fixed. So we are going to study a family of problems of non-local type, but depending on a parameter. We try to study the same attractors that I have not proved still how they are well posed. And we are trying to study the robustness of this attractor. The kind of assumption on the boundary sometimes are more weakened, and some other times are assumed to be slightly strong to avoid this difficulty. But at this stage, I have put without condition on the boundary because we are dealing with homogeneous Dirichlet boundary condition. So consider this kind of condition. A is the function controlling the non-local term. It is having values between little m, that is strictly positive, and some capital M. The capital M, immediately, if we have a good sign condition on F, is not going to be necessary, okay? The capital M can be removed because we are going to obtain immediately after Gromwald lemma with the first equality, the first energy equality, where we are going to obtain L infinity in time estimates L2 of omega. So we can remove about that condition because we are going to live always in a bounded set. Because U is going to be in L infinity, L is acting on U, and all this quantity is going to move between some values. So the M is going to appear by 3. The epsilon that it is in front of the terms in the equation is just put for simplicity. In posterior slides, I will change to other condition. The F satisfies the standard non-linearity condition in some papers in the literature with reaction-diffusion terms, like this. The initial time where the problem starts is at not necessarily 0 because we have one extra term, if you can see in the top, in the right-hand side, that is H, that depends on time. Our problem is going to depend on time. It's not just autonomous problem. It's a non-autonomous problem. H is going to have the regularity L2 local in R with values in H minus 1, at least for weak solution. We use the standard identification L2 with its dual, the H1 0 intersection LP, and we obtain the standard weak solution L2 in time H1 0, LP, and L infinite time L2 in omega. This extends the similar results for the first sublinear paper we'll deal with. This is the condition, the notion of solution. We have the good regularity for U prime. We can therefore consider one representant continuous in time with values in L2 of omega. So the initial datum makes sense. And the energy equality that this is our main tool can be used. From this energy equality applied carefully to the Galerkin approximation, we can use it to derive the compactness method and to obtain the system of weak solution for the problem, and even to obtain the existence of attractors, as we will see in a posterior slide. This is the theorem concerning the existence of weak solution. We have forget now about the uniqueness. Okay, I just put that for a flavor. And it just relies on the standard a priori estimates. We are multiplier people, and obtaining a priori uniform estimates from the Galerkin approximation and passing through the limit and identifying what are the weak limits. If we can use Aubin-Lyon lemma, we are fine. If we can obtain this by other conditions like translation compact criterion, we are fine too. So after this slide, we have good relative compact results for the sequence of Galerkin solution to the problem. And for the subsequence, reliable the same, it converges strongly actually in L2 in time, L2 in space. We can identify the weak limit, and we can pass to the limit. If you think about the way of passing to the limit, it is not complicated. Even if we have the non-local term in front of the Laplacian, we can pass, for instance, weakly of A L of un towards A L of u times u, and then by distribution theory we can identify. There are many other ways to pass to the limit with a test function suitably to obtain that we can identify what the weak limit actually of the problem. So we obtain a solution in an interval from t to t to capital T, and we can concatenate solution and obtain global in time solution. Well, at this stage, what happens if we want to go further in the analysis of the dynamic of the solution and we don't have so good condition as we put previously with the stationary solution? What happens if we have that the little m is not big enough? Sometimes when we have a dissipative problem, but it is not so strong, such that there's a global exponentially uniform attracting solution, the problem still is well posed. It poses a global solution in time, and we can define a semi-flow, and we have that the semi-flow, that is a semi-group, satisfied good conditions such that we can define a global attractor. This is the nice dream at the end of the 60s and of the 70s by many mathematicians. A compact attractor for autonomous problem, this is a theoretical, okay? This is different from the application we are concerning. A global attractor is a compact set in my space X that has to be invariant through S. I mean, for any time A is going to be equal to the set of solutions starting at A at the time T, and attracts all the dynamic starting in bounded sets. So it is robust. With respect to B, it satisfies that the Hausdorff semi-distance goes to 0. So the attractor generalizes what should be an attracting point, but it may contain much more complex dynamics. When a global attractor exists, of course, it is unique. It is a maximal compact invariant set. It is the minimal closely attracting set of bounded sets. It is composed by complete bounded orbits. I forgot that to put bounded orbits. It has its own dynamic. You can prove under suitable extra assumption that it have finite Hausdorff fractal dimensions, and after some result by Magnet, you can obtain a finite parametrization, even if your problem is finite, it's infinite dimensional. If I come from a PDE, there are so big names. I just put here some few of them, starting from the Russian school, Leisenskaya, Babin, Bichik, Hale, your Brazilian colleague, Professor Ricardo Rosa, and many others. But the problem is that the autonomous situation where your differential problem coming from the beginning at the top of the slide is autonomous, it doesn't have an explicit dependent on time. It's not the case always. Sometimes we have problems that depend intrinsically from the time because of noise perturbation, random perturbation, any other type of situation. For instance, a problem that is moving in not a fixed domain but a non-cylindrical domain, something that Professor Horst has also done in a very famous book. So there exist many other kind of attractors that are not relying in the concept of global attractor, also called compact attractor, but skew flows, uniform attractor, but are time dependent, as Chepisok and Ilin or Chepisok and Vishik, random attractor by Smalfuss, Frondoli, De Bush, Arnold, and the German school, Peter Kloeden, another good colleague and friend, Alexandre Carvalho. There are many colleagues that they study non-autonomous dynamical system and need to extend the concept of global attractor to a situation where the problem depends on time. So if you remember this only abstract slide, I put an initial problem where H was depending on time. I'm interested in a problem that it is moving on time. And so I'm forced to use some of the possible extension of attraction. The extension we have used is related similarly to the cocycle attractor for random dynamical system, but in the deterministic case, we call that pullback attractor. For a pullback attractor, we firstly need to have a process. A process has two times, the final time, but also the initial time. This is a generalization of the semi-group property called the cycle property or the process property. Because we don't have uniqueness of solution, we have a multi-valued process. And it means that my solution also, it starts with a single value. It may have possible multiple solutions, and I'm moving along sets. This is important, for instance, if we are trying to thinking about the Millennium Problem in physics, in mechanics, in fluid mechanics, in 3D Navier-Stokes, for instance. But because we have A not so regular, and maybe F sometimes doesn't satisfy a good quasi-ellipsis condition, I lose the uniqueness property. So I try to adapt the condition ensuring the system of attractor, the continuity notions, the absorbing family, and the asymptotic compactness in the autonomous case to the non-autonomous case. I will skip this quickly. I don't want to make over in time very long. So for a multi-value process, it's possible to define a concept of continuity. Actually, it's possible to define several concepts, upper and lower semi-continuity. But for us, it is enough if we have upper semi-continuity. For a universe that it is attracted by some object that is going to be the family of attractor, we are also allowed to have family moving in time, because if the time is part of our problem, we want that our conditions are moving in time. This is also influenced and useful from random dynamical system. A universe attracted in our setting, sometimes it is useful that satisfy that it's inclusion closed. It means that the family parameterized in time is inclusion closed if a family with section in time controlled or included in one family D for each time that belongs to the universe, then this D hat prime family of sets is also belonging to D. This is inclusion closed. The concept of absorbing, but in a pullback sense, means I consider that my dynamic is going to be frozen in the present time, okay? And I'm trying to fix the idea of what attractor I'm going to obtain if I pull back the initial time towards minus infinite. This is the whole concept of the pullback attractor. That's because of the name. The attractor is not going to be the attractor in the infinite. It's not going to be as the uniform attractor of Chebyshov-Vesic, but it's going to be an attractor that attracts the dynamics in the sense that if I fix the present time t, then I consider what trajectories, what solutions are attracted by some objects when the initial time goes back and back towards minus infinite. In the autonomous case, it's equivalent. But in the non-autonomous case, this is a generalization, more weaker, with weaker conditions than the uniform attractors of Chebyshov and Vesic. An absorbing, a pullback absorbing family is a family that absorbs in the pullback sense. A pullback asymptotically compact process is a process that satisfies a relatively compact property in a pullback sense, when the initial times tau n goes to minus infinite. An attractor, a pullback attractors with respect to some busting of attractions are family some universe D, is a family moving in time that is compact each section. It is attracting in pullback sense the elements of the universe. It is negatively invariant. And if possible, we will be happy if it is invariant. Actually, we will obtain an equality, not only a negatively invariance property. And it is minimal, because otherwise the pullback attractors are not necessarily unique. the minimal pullback attractor, and that's the only way to obtain uniqueness, if not we have counterexamples, is to obtain the minimal pullback attractor composed by the union of all the omega limit sets at any fixed time t. This is the analogous extension of the omega limit sets in the autonomous setting. What we do need to obtain the existence of attractor? Again, the two first ingredients, the absorbing property, pullback absorbing property, and pullback asymptotically compact condition. And in order to do that, we need to obtain good uniform estimates in the same way as for the system of solution. So this is the abstract theorem that says that the minimal pullback attractor is given by the union of all the omega limit sets when the process is asymptotically compact. And actually, if the process is strict, which is a property that usually holds when the translation of property holds and the solution are continuous, then our attractor is strictly invariant. The minimal pullback attractor in the L2 setting, in L2 of omega, for the family of problems P epsilon, the non-local problems P epsilon, is something more or less standard. I'm trying to skip here quickly, okay, in these slides. The process defined by the weak solution of the problem, defined as strict multivalued process, in the limit when epsilon goes to 0, actually it is a semi-flow, it is autonomous. We have good conditions concerning that the solution of every P epsilon problem satisfies some continuity. And the idea of the proof of all these continuity results come again by compactness argument and energy method. Oh, sorry, I didn't say something that it is important. The kind of condition in our right-hand side are not in order to obtain a compact absorbing family or a compact absorbing set. We rely on energy methods. Energy methods that I just described briefly means that we use the minimal absorbing condition, the minimal absorbing result, and we rely on weak convergence and convergence on the norm thanks to the energy functions associated to the problem. This is an idea developed by Ball originally in a damped dissipative wave equation and later adapted for Navier-Stokes by Ricardo Rosa, Professor Rosa, in a famous paper in nonlinear analysis in 1998. Then, with this continuity result, we are able to obtain that each single process, multiple process U epsilon, is upper semi-continuous and it works well with closed values. Now we are able to obtain the first of the two ingredients. We obtain one standard estimates of L infinity in time of L2 norm. The norm with one bar is the L2 norm. And the norm with double bar means the H1 norm when it appears. The norm H double bar H star that appears in the right-hand side means the norm in H minus 1. We obtain immediately by the energy equality this estimate. If you consider in this estimate that you have a good assumption concerning the integral in the right-hand side, you observe that the exponential may kill the initial data U2 appearing at the beginning of the right-hand side, okay? Then this gives us the idea of what is the type of universe we must describe to have an absorbing condition. The absorbing condition must be related to a universe moving in time where the exponential of some parameter mu, exponential of mu tau, is controlling the growth of the L2 norm of every section in D tau as initial condition in L2 norm. If we have that, and we have this number 2 condition, we have that H is controlled in the improper integral for some weight, for some mu epsilon 0, then we are able to obtain an absorbing family. This is going to be given in this proposition, saying that the family D epsilon 0, that it is the closed ball in L2 with radius rho epsilon square appearing by this expression, is going to be the absorbing family, the first ingredient for the problem. The second ingredient, the ingredient concerning the asymptotic compactness, comes by the energy method. I have explained it before, by uniform estimates, a bit tedious estimates, in the solution of the problem with some uniform amounts, rho 1 epsilon, rho 2 epsilon, etc., etc. These amounts appear described here, but you can forget about that. But believe me, they are controlled uniformly. So they make that we at least are able to consider for any family B belonging to the universe that when times tau n goes to minus infinite in the present time t, or in an interval concerning with the present time t, these are uniformly bounded. Then we are able to obtain the asymptotic compactness by the energy method that I'm going to skip and not to describe here. That this is related with energy functional, how we control the energy of the problem. Then we obtain the existence of attractor in many different universes. But these results are related with every single conception of the P epsilon problem. So we have a family of attractors. And the second purpose of the study we developed was to try to obtain a robustness results on the attractors when the parameter epsilon goes to 0. We can relate the attractor by some comparison results. I'm going to skip this part because I think I'm nearly to be over. And the problem is that in the end, we are able to obtain an attractor for the P0 problem, or the problem in the limit when epsilon is 0. We are able to obtain continuous dependence on a sequence solution with the epsilon problems with a suitable subsequence towards a solution of the P0 problem. And we are able to obtain the robustness, the upper semi-continuity result, saying that all the attractors that we have obtained with respect to the P epsilon problem in L2 norm are converging or are included in the upper semi-continuous sense inside the A0 attractor of the P0 problem. So that was the type of robustness result in L2. All this can be developed for more general type of coefficient in front of our problem, some term G1 depending on epsilon that goes to 1 when epsilon goes to 0, some G tilde 1 going also to 1 when epsilon goes to 0, and some G0 epsilon that goes to 0 when epsilon goes to 0. So I just put at the beginning the P epsilon problem for simplicity. We can do this much more complex using more regularization of the solution and dealing with the H1 norm. The problem is that I think I'm having much more of the time I should be, and I think that maybe I should stop here and not show this kind of other extension and the problem. Just before to finish, I would like, if you don't mind, to forget about all posterior regularity and all in H1, but to put the present slide about what is the problem of including a non-local term in the equation. Forget for the moment about the non-local equation we have been considering in the talk, and consider a standard problem like the one that it is written here in the middle of the slide. The standard reaction diffusion problem, ut minus Laplacian of u equal to f of u, f satisfying the assumption above, plus h. For simplicity, h with values in L2 of omega, okay? If you multiply formally by ut, you can do it rigorously by Galerkin and passing through the limit, you obtain that all the term with the minus Laplacian of u can be put inside some Lyapunov function, because you can consider it as the derivative in time of the L2 norm of the gradient. So in the end, if you integrate now in time, you obtain that ut in L2 is controlled by all these terms. Recall that your solution, even your weak solution, was in LP, but your strong solution is even more regular. So since the right-hand side here is going to be bounded, means that ut is going to be an element in L2 in time of L2 in space. That means that f of u is also there. If you have a non-local problem, you cannot use this trick. You cannot multiply by ut and obtain a simplification. So you don't have that f of u is going to be controlled. And you need to impose more condition on the nonlinearity to use as much as you can the subcritical or the critical Sobolev embedding on the regularity of the solution to try to strengthen how and to obtain that f of u is going to be an element of L2 to obtain a stronger second energy equality and to obtain a stronger robustness condition in L2. But that is the other half of the story that I have skipped. I don't want to put that. And so I think I should stop here. So thank you very much.
Okay, thank you, Professor. Are there any questions or comments?
Hi, Professor Pedro. Can you hear me?
Yeah, I can hear you. Not so well, but I can hear you, I think, more or less.
I have a curiosity about the problem you exposed. The equation is a quasi.
It's what? Sorry, Bruno? I can't hear you very well. It's what? Could you repeat, please? Bruno, can you hear me? Hello?
Can you hear me now?
Yeah, right now. Before I couldn't. Sorry, could you repeat, please?
Sure. The equation is quasi-linear. Is it right? Que la ecuación es casi lineal.
It's the problem. Yeah, is some sense. In some sense, it is quasi-linear in some sense, and you need to. Yeah. Well, I skip all concerning that and put again the beginning of the problem. The problem is that when you consider some element in front of that, probably speaking, you cannot apply immediately all the results. For instance, in any standard theory of the different theories, you can use directly the compactness, but because you need a stronger estimate that sometimes you don't have, you cannot use it directly semi-group because it is now non-linear, and you will need to perform a change of variables. Sometimes it works. We can try, even if it was funny for us, because it is a quite simple problem that it is very, very far from the Keller-Segel models that are much more complex, but it contains difficulties that make that we could not pass through a clear analysis to the existence of regular solutions. For which solution it is fine, but when the solution is not so regular, we need nonlinear semi-groups or some extra clever change of variables on different ways of deal with, but they are not so clear. That's the main difficulty that we try to expose.
But for f and h equals 0, could you use the approach in the Amos book for evolution family of operators?
I'm not very sure because I can hear you very well, to be honest. Sorry. But I mean, I think you have said if I can use the Lyapunov strategy of what? Of where?
If you can use the approach by in Amos book, the book
of Hammond.
Yeah.
I don't know. Certainly one of the way we're trying to explore now is to embed it completely in nonlinear semigroup. Yeah, it's true. It's true. With different mild solution setting. Yeah, exactly. In the way of Hammond. But the problem is that I came from another school. I came from French school, let's say, from Jean-Louis Lyon, you know, because of the time you spent here. And the problem is that I'm not so related as strongly as you are and other people with the SAME group and the AMAN and all that stuff. But we are trying to slow down now that way. Yeah, you're right. You're right.
Okay. I will leave time for the questions. Thank you very much.
Okay. Thank you to you.
Okay, are there other questions, comments? No? If not, let's thank Professor Pedro again. Thank you, Professor.
See you.
Result tomorrow, I think, at 9, right?
Yeah.
Bom, pessoal, então, com a saúde de hoje, eu esqueci um pouco puxado. Aí eu queria que quem vai para o hotel me acompanhe, porque a gente vai pegar o transporte para ir para o hotel, certo? Para se arrumar para ir para adiante. E amanhã a gente está de volta. E se amanhã não vai passar que horas para pegar? Almoço. Amanhã vai passar que horas? Foi o periquito canta e o papagaio fala e o periquito vai na sala agora. Não foi aqui. Foi, tá bom, já pensou. Vou lá.